Water is so familiar that it almost disappears from notice. It waits in glasses, clouds, rivers, pipes, cells. It cools engines, softens landscapes, carries heat, dissolves minerals, shapes weather, and quietly makes life possible. It is the first substance most people learn the name of, and often the last one they think to question. And yet, beneath that familiarity, water refuses to behave like it should. Its solid form floats instead of sinking. Its liquid form holds heat far more stubbornly than similar substances. Its molecules cling, align, rearrange, and cooperate in ways that resist simple explanation. Even after centuries of careful measurement, precise experiments, and powerful simulations, water still occupies an unusual position in science. Not unknown, not mysterious in a dramatic sense, but incomplete. This is a substance that has been examined by generations of chemists, physicists, biologists, and planetary scientists. It has been measured, modelled, frozen, boiled, compressed, stretched, illuminated, and simulated in extraordinary detail. And still, at its most fundamental level, liquid water remains one of the hardest everyday materials to fully describe. That tension is what this video explores. Not water as a symbol or a metaphor or a miracle, but water as a real physical system shaped by simple rules that somehow give rise to unexpectedly rich behavior. A substance that helped science learn how to measure the world, and that continues to remind science of its limits. So as this video unfolds, it moves slowly, from what is firmly known into what is still being debated, from structure to behavior, from molecules to planets, from certainty to open questions. There is no rush to resolve anything here, only an invitation to notice how something so ordinary can remain so deeply unfinished. Welcome to the Sleepy Scientist. If you enjoy calm, thoughtful science like this, consider liking the video and subscribing to the channel. And if you're listening or watching right now, feel free to share where you're joining from, whether it's somewhere shaped by oceans, rivers, rain, or simply a quiet glass of water nearby. Water entered science quietly, long before laboratories looked like laboratories at all. Before instruments, before standardized units, before glassware and calibrated scales, there was a need to understand matter in a way that could be compared, repeated, and trusted. And water, simply by being everywhere and behaving consistently enough, became one of the first substances through which people learned how to measure the world. In the ancient Mediterranean world, water was treated as one of the classical elements. It was grouped alongside earth, air, and fire, not as a substance with internal structure, but as a basic category of existence. In that view, water did not need explanation in terms of smaller parts. It simply was what it was, wet, flowing, heavy, and naturally seeking its level, useful, familiar, and philosophically complete. That way of thinking was powerful, but it placed limits on curiosity. If water was elemental, there was little reason to ask how it behaved internally, or why its properties were so consistent. Measurement mattered less than meaning. Explanation mattered less than classification. A different approach began to emerge centuries later, particularly within the scientific traditions of the Islamic Golden Age. Scholars working across regions that stretched from Central Asia to the Eastern Mediterranean began to treat water not as a philosophical given, but as a physical substance that could be quantified, compared, and tested. Al-Biruni, writing around the year 1000, carried out careful measurements of density using water as a reference. He compared the mass of equal volumes of different materials by observing how much water they displaced, producing remarkably accurate values by modern standards. This was not abstract philosophy. It was experimental method. Water, in this context, was no longer an element. It was a tool. Ibn Sina, known in the West as Avicenna, approached water from a medical and physical perspective. He described its role in bodily processes, its effects on temperature, and its capacity to dissolve substances. He treated water as something whose properties could be observed, not assumed. Heat transfer, purity, and interaction with other materials became practical questions, not philosophical ones. What mattered in this shift was not that these scholars solved the nature of water. They did not. What mattered was that water became a stable reference point, something reliable enough to build other measurements around. From there, water slowly became an epistemic anchor, a substance against which uncertainty could be reduced. As experimental science developed in early modern Europe, this role expanded. When thermometers were first constructed, water played a central part. Temperature scales were defined using water's phase changes. The freezing point and boiling point of water under standard atmospheric pressure became fixed reference markers. These were not chosen because water was special in a cosmic sense, but because it was accessible, repeatable, and behaved predictably enough to be useful. Purity, too, was often judged relative to water. Distillation techniques were refined to produce cleaner and cleaner samples of it. The ability to remove dissolved salts and impurities turned water into a test case for separation methods. If a laboratory could produce pure water, it could likely purify other substances as well. Mass standards followed a similar path. Early definitions of units such as the gram were tied to the mass of a specific volume of water at a specified temperature. Water, once again, was not the object of study. It was the ruler. This quiet role shaped scientific practice in ways that are easy to overlook. Water trained science to expect repeatability. It encouraged the idea that nature could be standardized, that a measurement made in one place could be trusted elsewhere, provided the same reference substance was used. Even as chemistry matured and the classical elements were discarded, water retained its central position. When Antoine Lavoisier helped establish modern chemical nomenclature in the late 1700s, water was no longer considered elemental. It was recognized as a compound. Hydrogen and oxygen combined in a fixed ratio. That discovery was transformative, but it did not demote water's status. If anything, it strengthened it. Water became proof that complex behavior could arise from simple composition. Two lightweight gases forming a stable liquid that flowed, froze, boiled, dissolved salts, and supported life. Yet even then, water's internal complexity was underestimated. Early atomic theory treated molecules as rigid objects. Bonds were fixed, structures were stable. Water fit neatly into diagrams and equations. What science did not yet appreciate was that liquid water is not a collection of isolated molecules. It is a constantly shifting network. Bonds stretch, bend, break, and reform on timescales far shorter than human perception. Order appears and disappears. Structure exists, but only briefly. Ironically, water's usefulness as a reference delayed recognition of its deeper complexity. Because it worked so well as a standard, it was easy to assume it was well understood. The assumption lingered quietly in the background of scientific progress. Throughout the 19th century, water continued to anchor new techniques. Calorimetry, the measurement of heat, relied heavily on water because of its unusually high capacity to absorb energy without large temperature changes. Once again, water was chosen not for mystery, but for stability. In laboratories, reactions were heated and cooled in water baths. Samples were stored, diluted and transported in aqueous solutions. Biological research depended on water to keep tissues viable. Geological studies used water flow to model erosion and sediment transport. In all these cases, water was the medium, the backdrop, the assumed constant, and that assumption shaped habits of thought. Scientific methods grew around water's apparent reliability. Instruments were calibrated using it. Procedures was designed with its properties in mind. The expectation formed that liquids, in general, could be treated similarly. That their behavior could be averaged, smoothed, and simplified. Only later did it become clear that water is a poor representative of liquids as a category. Many of its most useful properties are precisely what make it unusual. Its density anomaly, where the solid form is less dense than the liquid, is rare. Its surface tension is unusually high. Its heat capacity exceeds that of most comparable substances. Its ability to dissolve ionic and polar compounds is exceptional. These traits were known individually, but their deeper origin was not pursued with urgency. After all, water worked. What emerges, looking back, is a subtle irony. Water helped science learn how to measure, standardize, and control the physical world. It trained generations of researchers to trust experimental consistency. It anchored definitions of temperature, mass, and purity. It made laboratories possible in their modern form. At the same time, that very familiarity masked unresolved questions. Water became the substance through which science learned confidence, even as it quietly resisted complete description. This is not a story of ignorance. It is a story of success creating blind spots. Water did not just shape theories about matter, it shaped scientific behavior itself. It influenced what counted as a good experiment, what counted as reliable data, and what kinds of complexity were worth confronting. Only much later did researchers begin to realize that the substance they trusted most might be the one that challenged their assumptions most deeply, and that realization did not arrive as a dramatic discovery. It arrived slowly, through inconsistencies, anomalies, and models that worked almost perfectly, but not quite. Water had done its job too well. It taught science how to measure the world before science was fully prepared to measure water itself. At first glance, water looks like the easiest possible problem. Two hydrogen atoms, one oxygen atom joined together in a small, tidy arrangement. No long chains, no branching structures, no exotic elements. Compared to the sprawling molecules of biology or the complex lattices of solid materials, water seems almost modest. It appears to be the kind of system that should give up its secrets quickly. For a long time, scientists expected exactly that. In classical chemistry, molecules were imagined as small mechanical objects. Atoms were treated like beads connected by stiff links. If the parts were known, the behavior should follow. This way of thinking worked surprisingly well for many substances, especially gases, where interactions are weak and brief. It also worked well enough for solids, where atoms vibrate around fixed positions. Water, however, began to resist that simplicity as soon as scientists tried to describe it at the atomic scale. In the early 20th century, chemistry and physics were undergoing a quiet revolution. Classical ideas about atoms and bonds were giving way to quantum mechanics, a framework that replaced certainty with probability and rigid trajectories with wave-like behavior. Chemical bonds were no longer just connections. They were shared states, governed by the mathematics of quantum theory. Among the scientists shaping this shift were Walter Heitler and Fritz London. In the year 1927, they published work explaining the chemical bond using quantum mechanics, showing how electrons could be shared between atoms in a stable configuration. Their ideas laid the foundation for modern molecular theory. Water was one of the simplest test cases for this new understanding, and yet even here complications appeared immediately. The bond between oxygen and hydrogen is not evenly shared. Oxygen pulls more strongly on the electrons, creating an uneven distribution of electrical charge. This asymmetry gives the water molecule a permanent polarity. One side is slightly negative, the other slightly positive. At the level of a single molecule, this seems manageable. Polarity can be measured. Bond angles can be calculated. Energies can be estimated. Quantum chemistry handles this part of the problem well. The difficulty begins when molecules stop being alone. A glass of water does not contain a handful of molecules. It contains on the order of 10 sextillion molecules. That is a 1 followed by 22 zeros. Each of those molecules interacts with its neighbours through electrostatic attraction, repulsion, and short-range quantum effects. None of these interactions is especially strong, but there are so many of them that they dominate the behaviour of the liquid. This is where classical intuition begins to fail. In simple systems, understanding the parts often leads directly to understanding the whole. Double the number of molecules, and many properties double as well. Add more energy, and temperature rises in a predictable way. These linear relationships are comfortable. They scale cleanly. Water does not. Small changes at the molecular level can produce large nonlinear effects at the macroscopic level. Cooling water slightly can make it expand rather than contract. Adding heat does not raise its temperature as efficiently as it does for other liquids. Freezing rearranges molecules into an open structure rather than a compact one. These behaviors do not arise from individual molecules. They arise from coordination. Physicists refer to this as a many-body problem, a situation where the behavior of a system cannot be reduced to the sum of its parts, because the interactions between those parts matter as much as the parts themselves. In a two-body problem, such as a planet orbiting a star, equations can be written down and solved exactly. In a three-body problem, the solutions become unstable and sensitive to initial conditions. With many bodies, exact solutions vanish entirely. Patterns emerge, but they must be described statistically rather than precisely. Liquid water is a many-body system of staggering complexity. Each molecule forms temporary associations with several neighbours through hydrogen bonding. These bonds are weak compared to covalent bonds, but they are directional and cooperative. When one bond forms, it influences the likelihood of others forming nearby. Networks appear, dissolve, and reappear on timescales of trillionths of a second. At any given moment, the liquid contains regions that resemble ice, regions that resemble disordered fluid, and everything in between. These regions are small and short-lived, but they matter. They influence density, viscosity, heat capacity, and the way sound and light move through the liquid. From a distance, water looks smooth and uniform. At the molecular level, it is restless. This restlessness is not noise, it is structure in motion. Quantum chemistry can describe the interactions between a few molecules with impressive accuracy. Statistical mechanics can describe average behavior across many molecules. The challenge lies in the bridge between them, the point where individual quantum interactions give rise to collective classical properties. This is why simplicity at the molecular level does not guarantee simplicity at larger scales. The rules do not disappear, they multiply. An individual water molecule behaves one way in isolation. Place it in a cluster, and its electronic environment changes. Place it in a dense liquid, and its identity becomes inseparable from its surroundings. Properties that belong to the molecule alone give way to properties that belong to the network. In this sense, liquid water is not an object, it is a process. This perspective represents a shift in how scientists think about matter. Instead of asking what a molecule is, the question becomes how molecules coordinate, how patterns arise from interaction rather than instruction, how order emerges without design. Water was among the first substances to force this realization. It behaved too strangely to be explained by treating molecules as independent actors. It demanded attention to correlation, fluctuation, and collective motion. There is a quiet lesson here. Nature does not promise that small causes lead to small effects. It does not guarantee that understanding the pieces will automatically explain the whole. Water, despite its apparent simplicity, demonstrates this gently but persistently. 2 hydrogen atoms and 1 oxygen atom are enough to build a system that resists tidy explanation, not because it is exotic, but because it is deeply interconnected. This is not a failure of science. It is a boundary condition, a reminder that prediction becomes harder as cooperation increases. Water is simple only until it touches itself. Water's unevenness begins at the smallest scale, but it does not stay there. A single water molecule carries an internal imbalance. Oxygen pulls more strongly on shared electrons than hydrogen does, leaving one side of the molecule slightly negative and the other slightly positive. This is not a full charge, like that of an ion, but a partial one. The molecule becomes a dipole, with a built-in orientation and direction. On its own, that detail might seem minor. Many molecules have uneven charge distributions. What makes water distinctive is how strongly those dipoles influence one another when many molecules are brought together. In liquid water, every molecule is surrounded by others that are also unevenly charged. Each dipole feels the presence of its neighbours. They rotate, shift, and reorient in response, constantly adjusting to local electric fields created by nearby molecules. This collective sensitivity gives rise to one of water's most important properties, its dielectric behaviour. Dielectric behaviour describes how a material responds to electric fields. In simple terms, it measures how well a substance can reduce, or screen, electrical forces between charged particles. Water is exceptionally good at this. Its dielectric constant is high compared to most liquids, meaning that electric charges immersed in water feel each other far less strongly than they would in air or vacuum. This screening effect is not passive, it emerges from motion. When a charged particle enters water, surrounding molecules rotate so that their oppositely charged ends face it. This reorientation partially cancels the particle's electric field. The charge becomes wrapped in a responsive cloud of aligned dipoles. The field still exists, but it is softened, spread out, and moderated. This behaviour was explored in depth by Lars Onsager in the mid-20th century. Onsager developed theoretical descriptions of dipoles in polar liquids, showing how long-range interactions arise not just from individual charges, but from the collective response of many molecules acting together. His work helped clarify why water cannot be treated as an inert background. Its molecules actively rearrange themselves in response to their environment. The consequence of this is subtle but profound. Water does not merely host chemical reactions, it reshapes the forces that drive them. Ions dissolve in water because the liquid stabilizes separated charges. Positive and negative ions are pulled apart not by magic, but by the energetic benefit of being surrounded by oppositely oriented dipoles. The screening effect lowers the energy cost of separation, making dissolution favourable. Acids and bases behave differently in water for the same reason. Protons do not wander freely. They move through a constantly shifting network of hydrogen bonds, hopping from molecule to molecule in a process known as proton transfer. Water participates directly, rearranging itself to enable motion. Even neutral molecules are affected. Polar compounds dissolve readily because their charge distributions align with those of surrounding water molecules. Nonpolar substances struggle because they disrupt the local dipole organization without offering compatible interactions in return. In this way, water acts less like a container and more like a collaborator. This idea represents a departure from earlier chemical thinking. In classical reaction schemes, solvents were often treated as background conditions. They provided space, temperature control and mixing, but did not fundamentally alter reaction pathways. Water resists this simplification. Its polarity means that every reaction occurring within it is embedded in a responsive electrical environment. Forces are screened, amplified, redirected, and reshaped by the surrounding liquid. Energy landscapes change, transition states shift, reaction rates adjust. The medium becomes part of the mechanism. This responsiveness extends beyond chemistry into larger scale organization. Because water's dipoles interact over relatively long distances, patterns of alignment can propagate through the liquid. These patterns are fleeting, but they influence bulk properties such as viscosity, surface tension, and the way water responds to external fields. Onsage's work emphasized that long-range order does not require rigid structure. Correlations can exist without permanence. Molecules do not need to lock into place to influence one another. Statistical alignment is enough. This is why water behaves coherently without becoming solid. At any moment, regions of the liquid exhibit partial alignment of dipoles. These regions form and dissolve continuously. They are shaped by temperature, pressure, dissolved substances, and nearby surfaces. None of them last long, but together they give water its characteristic behavior. The result is a liquid that senses and responds. Introduce salt, and water reorganizes to stabilize ions. Introduce heat, and molecular motion disrupts alignment. Introduce an electric field, and dipoles rotate collectively. Introduce a surface, and nearby molecules adopt preferred orientations. Water is not indifferent, it reacts. This sensitivity allows water to support complex systems. Biological molecules rely on it to moderate forces that would otherwise tear structures apart. Charge groups on proteins remain stable because water softens their interactions. Membranes form because water reorganizes itself around nonpolar regions, effectively pushing them together. None of this requires intention or design. It arises from polarity interacting with density and motion. What makes this remarkable is that the same underlying property explains phenomena across scales. The uneven charge distribution of a single molecule influences the behavior of oceans and cells alike. It shapes how clouds form, how minerals dissolve, how nerve signals propagate, and how enzymes function. The link between microscopic polarity and macroscopic order is not linear. Small changes in alignment can lead to large shifts in behavior. Temperature, for example, affects how easily dipoles can reorient. As thermal motion increases, alignment becomes harder to maintain. Dielectric screening weakens slightly. Reaction rates change. These effects are measurable. They are predictable in broad terms, yet they remain difficult to calculate precisely because they depend on collective motion rather than fixed structure. Water, in this sense, behaves more like a responsive fabric than a static material. It stretches, relaxes, and redistributes forces dynamically. It does not simply transmit interactions, it modifies them. This is why treating water as a passive background leads to misunderstanding. It is not a neutral stage on which chemistry unfolds. It is an active participant that shapes what is possible. The uneven balance within each molecule scales upward into an uneven balance across the entire liquid. Order and disorder coexist. Stability emerges from motion. Screening arises from responsiveness. Polarity does not just explain why water dissolves salts or conducts electricity weakly. It explains why water organizes systems without rigid structure, why it supports complexity without freezing into place. Water's charge imbalance never resolves. It persists, fluctuates, and propagates. And in doing so, it turns a simple molecule into a medium capable of shaping entire systems. The imbalance is not a flaw. It is the source of water's quiet influence, and once noticed, it becomes impossible to ignore. The strange power of water does not come from strength. It comes from cooperation. At the heart of that cooperation lies a subtle interaction known as hydrogen bonding. It is weaker than the bonds that hold atoms together within a molecule, yet far more influential than its modest strength would suggest. Hydrogen bonds are temporary directional attractions between slightly charged regions of neighbouring molecules. In water, they appear everywhere, all the time. Each water molecule is capable of forming several hydrogen bonds at once. The positively charged hydrogen atoms are attracted to the negatively charged oxygen atoms of nearby molecules. These attractions pull molecules into loose associations, forming local groupings that resemble structure without ever settling into permanence. Early attempts to understand this behavior focused on individual bonds. Linus Pauling helped clarify how hydrogen bonds arise from electronic structure and why they favor specific orientations. His work established hydrogen bonding as a real, measurable interaction rather than a vague attraction. That alone was a major advance. But it soon became clear that knowing how a single hydrogen bond behaves does not explain what happens when trillions of them interact at once. In the 1930s, John Desmond Bernal and Ralph Fowler approached the problem from a different angle. Rather than treating liquid water as a disordered version of ice or a compressed gas, they proposed that it possessed its own kind of organization, not fixed, not crystalline, but patterned. Their model suggested that liquid water contains transient networks of hydrogen-bonded molecules. These networks are constantly forming and breaking, reshaping themselves in response to thermal motion. There is order, but it's statistical rather than deterministic. This distinction matters. In a deterministic system, knowing the exact state of the components allows precise prediction of the whole. In a statistical system, only probabilities can be predicted. Individual configurations are fleeting, but average behavior becomes meaningful over time. Liquid water belongs firmly in the second category. At any moment, a given molecule may be bonded to several neighbours, one neighbour, or none at all. The exact arrangement changes on timescales of trillionths of a second. Bonds stretch, rotate, and snap, only to reform elsewhere. No single configuration defines the liquid. The behaviour emerges from the constant turnover. This is what is meant by fluctuating order. There is structure, but it is not fixed in space. There is organisation, but it does not persist in time. Patterns exist as tendencies rather than blueprints. It can be tempting to imagine the hydrogen bond network as a loose scaffold that fills the liquid. That image is useful, but incomplete. The network is not a static object. It is better understood as a continuously reconfiguring field of interactions. Each hydrogen bond influences the likelihood of others forming nearby. When a molecule participates in one bond, its ability to form additional bonds changes. Angles shift. Charges redistribute slightly. The local environment adjusts. This cooperative effect means that hydrogen bonding in water is not a collection of isolated events. It is a collective phenomenon. Because of this, the network responds smoothly to changes in conditions. Increase the temperature, and thermal motion disrupts alignment. Bonds become shorter-lived. The average connectivity decreases, lower the temperature, and bonds persist longer. Networks become more extensive. Approaching freezing, the liquid begins to resemble ice not suddenly, but gradually, as local order becomes more pronounced. Pressure has its own influence. Compress the liquid, and the open structures favoured by hydrogen bonding are squeezed. Alternative arrangements appear. The balance shifts. Dissolved substances also play a role. Ions and molecules distort the local network, either stabilizing certain arrangements or disrupting them. The liquid adapts around them, reorganizing its bonding patterns to accommodate new participants. This flexibility explains why water can dissolve so many substances while still retaining its identity. The hydrogen bond network absorbs disruption without collapsing. It bends, rearranges, and continues. What makes this remarkable is that none of this behavior is programmed. There is no instruction set telling water how to organize itself. There is no preferred global pattern. Everything arises from local interactions repeated on an enormous scale. The collective behavior of hydrogen bonds gives rise to many of water's most familiar properties. Its unusually high boiling point, for a molecule of its size, reflects the energy required to disrupt the network. Its surface tension arises because molecules at the surface experience asymmetric bonding, pulling them inward. Its heat capacity is elevated because added energy goes into rearranging bonds rather than simply increasing motion. Each of these properties emerges from cooperation. Importantly, this cooperation is not perfect. It is noisy, incomplete, and constantly in flux. That imperfection is essential. A fully ordered hydrogen bond network would freeze into a solid. A completely disordered one would behave like a gas. Liquid water occupies the narrow space between, sustained by motion. This balance is difficult to capture mathematically. Models must account for directionality, fluctuation, and correlation across many molecules. Simplify too much, and the network disappears. Add too much detail, and calculations become intractable. Bernal and Fowler's insight was not that they had found the exact structure of liquid water. It was that structure itself had to be redefined. Liquid order could not be described by fixed positions or repeating units. It had to be understood in terms of probabilities and correlations. This realization opened the door to a broader idea in science: emergence. Emergence describes situations where complex behavior arises from simple rules without central control. The properties of the whole cannot be easily inferred from the properties of the parts alone. Instead, they arise from interaction, feedback, and scale. Hydrogen bonding in water is a textbook example. A single hydrogen bond is weak and fleeting. A vast population of them produces stability, coherence, and resilience. The liquid flows, yet resists compression. It adapts, yet maintains consistency. It supports life, yet remains chemically neutral. The network does not have a shape, but it has influence. Thinking of hydrogen bonding as a field rather than a structure helps make sense of this. Fields are defined not by fixed objects but by relationships. They vary smoothly in space and time. They respond to perturbations. They transmit influence without requiring rigid connections. In water, the hydrogen bond field is everywhere. It is the medium through which forces propagate and patterns emerge. It is what allows local events to have system-wide consequences. A single molecule joining or leaving the network does not matter. What matters is how that change ripples outward, subtly altering the probabilities of countless nearby interactions. This perspective shifts attention away from individual molecules and toward collective dynamics. It encourages questions about correlation length, fluctuation timescales, and cooperative motion. It invites tools from statistical physics rather than classical mechanics. It also explains why water continues to surprise. Systems governed by emergence rarely yield simple explanations. Their behavior is lawful but not obvious, predictable in outline but intricate in detail. There is a quiet humility in this realization. Water does not hide its secrets behind complexity of composition. It hides them behind cooperation, behind the fact that many simple things acting together can produce behavior that no single thing contains. Hydrogen bonds taken one by one are unremarkable. Taken together, they form a restless, adaptive network that underlies nearly every property of liquid water. The order they create is never fixed, yet never absent. It flickers, flows, and reorganizes continuously, sustaining a liquid that is stable without being rigid. From this fluctuating order, larger patterns begin to take shape. Properties emerge that belong not to molecules but to the system as a whole. And in that emergence lies the deeper challenge water poses to understanding. Among all of water's peculiar habits, one stands out because it is so visible, so familiar, and yet so quietly astonishing. Ice floats. In most substances, cooling causes contraction. Molecules slow down, draw closer together, and pack more tightly. Solids usually sink in their own liquids because their atoms are locked into dense arrangements. This behavior is so common that it feels like a rule. Water breaks it. As liquid water cools from room temperature, it behaves normally at first. Its density increases as thermal motion decreases. Molecules move less vigorously and settle closer together, but as the temperature approaches a few degrees above freezing, something unexpected happens. Instead of continuing to contract, water begins to expand. This phenomenon is known as anomalous expansion. It is one of the clearest signs that water does not behave like a typical liquid. At the freezing point, this expansion becomes dramatic. When liquid water solidifies into ice, its volume increases by roughly 9%. That may not sound like much, but at the scale of lakes, oceans, and planetary crusts, it is enormous. The reason lies in structure. As water freezes, hydrogen bonds become more stable and persistent. Molecules arrange themselves into an open, hexagonal lattice that maximizes hydrogen bonding rather than density. Each molecule locks into place with neighbors at fixed angles, creating empty spaces within the structure. These gaps reduce overall density. Liquid water, by contrast, is more compact. Its hydrogen bond network is constantly rearranging, allowing molecules to slip closer together on average. The result is a solid that is less dense than its liquid form. This behavior is sometimes described as negative thermal expansion near the freezing point. Instead of shrinking as it cools, water expands. This places it among a small group of substances that behave this way under certain conditions. The implications are far-reaching. Ice floating on water acts as an insulating layer. When lakes and oceans freeze at the surface, the ice slows further heat loss from the liquid below. Water beneath the ice remains liquid even as air temperatures drop far below freezing. This allows aquatic life to survive seasonal cold rather than being frozen solid from top to bottom. If ice sank, bodies of water would freeze from the bottom upward. Once frozen, ice would accumulate on the floor of the lakes and oceans, making thawing slow and incomplete. Over time, many aquatic environments would become permanently frozen. This single structural oddity shapes ecosystems on a planetary scale. But floating ice is only the most visible expression of a deeper pattern. Water's density reaches a maximum not at freezing, but a few degrees above it. As water cools from warmer temperatures, it becomes denser until it reaches that point. Cooling further causes expansion. Heating from that point also causes expansion. This density maximum influences circulation in lakes and oceans. It determines how water layers mix seasonally. It affects nutrient transport, oxygen distribution, and thermal stability. None of this behavior follows from simple intuition. The unusual properties of ice and liquid water under pressure add another layer of complexity. In the early 20th century, Percy Bridgman conducted a series of experiments subjecting water and ice to extreme pressures. He discovered that ice does not exist in just one solid form, but many. Under increasing pressure, water forms a succession of different crystalline ice phases, each with its own structure and density. Some of these forms are denser than liquid water. Others have unusual electrical or mechanical properties. These phases appear only under conditions far removed from everyday experience, but they reveal something important. Water's structural behavior is not fixed, it adapts. Bridgman's work showed that hydrogen bonding can reorganize itself in fundamentally different ways depending on pressure and temperature. The familiar hexagonal ice found in freezers and polar regions is just one possibility among many. In some high-pressure ice phases, molecules pack more tightly than in liquid water. In others, bonding patterns shift dramatically. The idea that ice floats is therefore not a universal rule. It is a contingent outcome of water's structure under specific conditions. This reinforces a key point. Water violates expectations not because it is inconsistent, but because it is flexible. Its behavior depends on the balance between hydrogen bonding, thermal motion, and pressure. Change the balance and new structures emerge. This flexibility extends to negative thermal expansion itself. The expansion upon cooling arises because hydrogen bonding favors open arrangements. At higher temperatures, thermal motion disrupts these arrangements, allowing denser packing. As temperature falls, bonding wins out over motion, and structure expands. This competition between order and motion runs through all of water's anomalies. It explains why water has a high heat capacity, why it resists compression, and why it behaves differently under pressure than most liquids. Ice floating is simply the most dramatic outcome of that competition. From a planetary perspective, these properties are not incidental. They influence climate stability, geological processes, and the long-term persistence of liquid water on planetary surfaces. On Earth, floating ice regulates heat exchange between the atmosphere and oceans. Seasonal freezing and thawing help redistribute energy. Polar ice reflects sunlight, affecting global temperature. Glaciers shape landscapes through erosion and deposition. Water's expansion upon freezing also fractures rock. When liquid water seeps into cracks and freezes, it expands, exerting pressure that breaks stone apart. This process contributes to soil formation and landscape evolution. It is slow, persistent, and powerful. Beyond Earth, these anomalies matter just as much. On icy moons such as Europa and Enceladus, different ice phases may exist deep beneath the surface, shaped by immense pressure. The behavior of ice under those conditions influences whether subsurface oceans can persist, how heat is transported, and whether chemical exchange with rocky interiors is possible. If water behaved like a typical substance, many of these environments would look very different. Ice would sink, liquid layers would be thinner or absent, heat transport would change, habitability would be far less likely. In this sense, ice floating is not a quirky detail. It is a structural signature of deeper molecular behavior that shapes entire worlds. It is tempting to view this as a fortunate coincidence, but from a scientific standpoint it is simply a consequence of hydrogen bonding and molecular geometry. No intention is required, no special tuning is assumed. What is remarkable is not that water behaves this way, but that such behavior emerges from such simple ingredients. 2 hydrogen atoms, 1 oxygen atom, a bond geometry that favours openness, interactions weak enough to rearrange, yet strong enough to coordinate. Together they produce a substance that expands when cooled, floats when frozen, and stabilizes environments across scales. Ice floating is the visible tip of a structural iceberg, revealing that water's most familiar behaviors are expressions of deeper, less obvious rules. Those rules do not simplify under extremes, they become more varied, more intricate, and more revealing. And through them, water continues to remind science that expectation is not the same as understanding. Water does something unusual with heat. It absorbs it quietly, stores it patiently, and releases it slowly. Most substances warm up quickly when energy is added. Their temperature rises in direct proportion to the heat they receive. Water does not follow that pattern. It has an unusually high specific heat capacity, meaning it requires more energy to raise its temperature than most other liquids. Roughly speaking, it takes several times more energy to warm water by a single degree than it does to warm substances such as ethanol or liquid ammonia. This property is not subtle. It dominates how water behaves across environments, from kitchens to climates. At the molecular level, the explanation again traces back to hydrogen bonding. When heat enters liquid water, much of that energy does not go directly into increasing molecular speed. Instead, it is absorbed by the continual breaking, bending, and reforming of hydrogen bonds. Energy is spent rearranging relationships rather than accelerating motion. Temperature, in other words, is buffered. This buffering has deep thermodynamic consequences. Heat input does not immediately translate into disorder. Instead, it is temporarily stored in the structure of the liquid itself. The system absorbs energy without dramatic change, remaining stable across a wide range of conditions. This is closely related to entropy, the measure of how energy and matter are distributed within a system. In many materials, adding heat rapidly increases entropy by increasing randomness of motion. In water, entropy increases more gradually because energy is diverted into reorganizing interactions rather than purely into motion. This behavior can be described as entropy buffering. Water moderates the pace at which disorder increases. That moderation matters. Large bodies of water resist rapid temperature change. Oceans absorb enormous amounts of solar energy during the day and release it slowly at night. Seasonal heating and cooling are smoothed. Coastal regions experience milder climates than inland areas at similar latitudes. Daily temperature swings are softened. On a planetary scale, this effect stabilizes climate, but the influence of heat buffering extends far beyond weather. It shapes the behavior of systems that operate far from equilibrium. Equilibrium describes a condition where energy flows have balanced out and nothing changes overall. Many interesting systems, including living organisms, weather patterns, and ecosystems, do not operate near equilibrium. They persist by continuously exchanging energy with their surroundings. Ilya Prigogine devoted much of his work to understanding such systems. He introduced the concept of dissipative structures, organize patterns that arise and persist in systems driven by continuous energy flow. Examples include convection cells in heated fluids, chemical oscillations, and biological metabolism. These structures maintain order not by avoiding entropy, but by exporting it. They remain organized by continuously dissipating energy. Water plays a central role in enabling this. Because water can absorb and release heat without large temperature swings, it provides a stable thermal environment in which far from equilibrium processes can operate. Energy can flow through the system steadily rather than violently. Gradients can be maintained without collapse. Consider a living cell. Metabolic reactions generate heat. If that heat were not managed, temperature would rise rapidly, disrupting delicate chemical processes. Water, which makes up most of the cell's mass, absorbs that energy and redistributes it. Temperature remains within a narrow range even as reactions proceed. The same principle applies to larger systems. In oceans, heat absorbed at the surface is transported by currents, slowly redistributed across vast distances. Energy enters, moves, and leaves without destabilizing the whole. This ability to stabilize instability is one of water's most important roles. It allows systems to exist in dynamic balance, not frozen, not chaotic, but persistently active. Without this property, many processes would be either sluggish or violent. Chemical reactions would overheat. Weather systems would become more extreme. Biological organization would be harder to sustain. Water does not eliminate instability, it manages it. From a thermodynamic perspective, this places water in a special category. It acts as a mediator between energy input and system response. It slows down transitions, spreads them out in time, and allows gradients to exist without breaking down immediately. This mediation depends on scale. At small scales, hydrogen bonding absorbs energy. At larger scales, bulk motion and convection distribute heat. At planetary scales, oceans and ice regulate energy exchange with space. All of these processes are linked. Entropy still increases. The laws of thermodynamics are not suspended, but the path entropy takes is shaped by water's properties. Disorder is produced gradually, channeled through flows rather than bursts. This has implications for how complexity arises. Complex systems require both stability and change. Too much rigidity, and nothing adapts. Too much fluctuation, and nothing persists. Water occupies a narrow middle ground. It permits constant motion without catastrophic transition. Prigogine emphasized that order can arise from non-equilibrium conditions. Water provides a medium where such conditions can be sustained gently. Energy flows through without destroying structure. Patterns form, dissolve, and reform. Even simple physical systems demonstrate this. Heat a shallow layer of water from below, and convection cells appear. Regular patterns of motion emerge spontaneously as the system transports energy upward. These patterns persist as long as the energy flow continues. The water does not resist the flow, it organizes around it. In more complex settings, the same principle applies. Rivers carve channels that persist while water flows. Atmospheric circulation organizes into stable wind patterns. Biological tissues maintain internal order while exchanging energy with their surroundings. In each case, water's thermal properties are central. This stabilizing influence also explains why temperature ranges compatible with life are relatively narrow. Water's buffering makes those ranges achievable. It keeps temperatures from fluctuating too rapidly, giving chemical and biological processes time to respond. There is a quiet elegance to this. Water does not impose order. It allows order to emerge by moderating extremes. It cushions systems against rapid change while remaining responsive to gradual shifts. From this perspective, water can be seen as a regulator rather than a controller. It shapes the conditions under which complexity can persist, without dictating specific outcomes. This naturally leads toward a systems view of nature. Instead of isolating components, attention shifts to interactions, flows, and feedback. Water links processes across scales. Molecular interactions influence cellular stability. Cellular processes influence ecosystems. Ecosystems influence climate. Heat moves through all of it. Water sits at the center of these flows, not as a passive conduit, but as an active participant that shapes how energy moves and how structures endure. The remarkable thing is how little drama accompanies this role. There are no sharp thresholds, no sudden switches. Water absorbs, redistributes, and releases energy continuously, quietly maintaining balance while allowing change. It stabilizes instability not by stopping motion, but by giving motion somewhere to go. In doing so, it creates the conditions under which systems can remain alive, dynamic, and resilient without ever settling into stillness. And that ability, more than any single anomaly, explains why water underlies so much of the organized activity seen on this planet and beyond. Water does not simply exist on a planet, it participates in how the planet behaves. To understand that participation, scientists began to move away from studying Earth as a collection of separate parts and towards seeing it as a connected system. This approach is known as Earth system theory. It treats the atmosphere, oceans, ice, land, and living organisms as interacting components, linked by flows of energy and matter. Within this view, water occupies a central position. It moves between reservoirs, changes phase, dissolves materials, transports heat, and links processes that would otherwise remain isolated. One of the most important ideas in Earth system science is the feedback loop. A feedback loop occurs when a process alters conditions in a way that then feeds back on the original process, either amplifying it or damping it. Water is involved in many of the strongest feedbacks on Earth. Consider temperature. As the planet warms, more water evaporates into the atmosphere. Water vapor is a greenhouse gas, meaning it absorbs infrared radiation and reduces heat loss to space. This creates a positive feedback where warming leads to more warming. At the same time, warming can melt ice. Ice reflects sunlight efficiently, while liquid water absorbs more energy. As ice retreats, the planet absorbs more solar radiation, reinforcing warming further. This is another positive feedback involving water. But not all feedbacks amplify change. Some counteract it. Increased evaporation also leads to more cloud formation. Clouds can reflect sunlight back into space, cooling the surface. They can also trap heat depending on their altitude and structure. The net effect varies, introducing a stabilizing complexity rather than a simple runaway. Water in this sense is not a thermostat with a fixed setting. It is a regulator whose effects depend on context. James Lovelock contributed significantly to this way of thinking by emphasizing that planetary conditions can remain within habitable ranges for long periods, despite external disturbances. While his ideas are sometimes associated with metaphors of planetary self-regulation, the scientific core is more restrained. It focuses on feedbacks, coupling, and long-term stability emerging from interaction, not intention. Water is central to that coupling. Geological processes release gases into the atmosphere through volcanic activity. Carbon dioxide enters the air, raising greenhouse warming. Over long timescales, water participates in counterbalancing this input through chemical weathering. Rainwater, slightly acidic due to dissolved carbon dioxide, reacts with silicate rocks at Earth's surface. These reactions consume carbon dioxide and produce dissolved ions that are carried by rivers to the oceans. There, carbon can be locked away in sediments over millions of years. This process is slow. It does not respond to short-term fluctuations, but over geological time, it provides a powerful stabilizing influence on atmospheric composition. Water acts as the transport medium that links atmosphere, land, and ocean in this cycle. Without liquid water flowing across continents, chemical weathering would be vastly less effective. Carbon regulation would weaken. Climate would drift more easily toward extremes. The oceans themselves are immense reservoirs of heat and carbon. They absorb roughly a quarter of the carbon dioxide emitted into the atmosphere by natural and human processes. They also store far more heat than the atmosphere, buffering surface temperature changes. Ocean circulation redistributes this heat across the globe. Warm water flows poleward near the surface. Cold water sinks and returns toward the equator at depth. This slow conveyor operates over centuries, smoothing temperature differences between regions. Again, water connects systems that would otherwise remain thermally isolated. Ice plays its own regulatory role. Glaciers and ice sheets respond slowly to climate change, advancing and retreating over thousands of years. Their presence influences sea level, ocean circulation, and surface reflectivity. Their slow response introduces inertia into the climate system, resisting rapid shifts. All of these processes unfold over vastly different timescales. Weather operates over days, ocean circulation over centuries, ice sheets over millennia, rock weathering over millions of years. Water participates in all of them. This multiscale involvement is what makes water such an effective planetary regulator. It does not enforce stability at a single time scale. Instead, it weaves together fast and slow processes, allowing the planet to absorb disturbances without immediate collapse. From a physical chemistry perspective, this regulation emerges from phase changes, heat capacity, solvent behavior, and transport properties. Nothing here requires special planetary tuning. The same molecular features discussed earlier scale upward through flow and feedback. Evaporation transfers heat from the surface to the atmosphere. Condensation releases it elsewhere. Dissolution moves ions from rock to sea. Freezing and melting redistribute energy and momentum. Each process obeys well-understood physical principles. What changes is their integration. Earth system theory emphasizes that no single process controls planetary behavior. Regulation emerges from interaction. Water is effective not because it dominates, but because it links. This linking role becomes clearer when comparing Earth to other planets. Mars shows evidence of past liquid water, but lacks a stable hydrological cycle today. Without sustained liquid water on its surface, chemical weathering slowed. Carbon dioxide accumulated or was lost to space without effective regulation. Temperature extremes became more severe. Venus, by contrast, may have lost its water early. Without it, there was no efficient way to remove carbon dioxide from the atmosphere. Greenhouse warming intensified, leading to surface temperatures high enough to melt lead. Earth occupies a narrow middle ground, not because water is rare, but because water remains active across surface and atmosphere. This activity does not guarantee stability forever. Feedbacks can shift, thresholds can be crossed, regulation can fail, but over billions of years water has helped maintain conditions suitable for liquid water itself. This circularity is not mystical, it is mechanical. Water moderates temperature, which allows liquid water to persist, which enables weathering and circulation, which stabilizes atmospheric composition, which maintains temperatures. The loop is physical, not purposeful. Importantly, this regulation is slow. It does not protect against abrupt change. It does not respond on human timescales. It operates through accumulation, delay, and gradual adjustment. That slowness is often misunderstood. Stability does not mean immobility. It means resistance to runaway change over long periods. Water's regulatory influence is best seen when viewed across deep time. Over hundreds of millions of years, Earth's climate has varied dramatically. Ice ages have come and gone, continents have shifted, oceans have opened and closed, yet liquid water has persisted on the surface for most of the planet's history. That persistence is not accidental. It reflects the cumulative effect of countless interactions mediated by water itself. From the scale of hydrogen bonds to the scale of continents, the same substance participates continuously. Its physical chemistry does not stop at the molecular level. It echoes upward, shaping flows, cycles, and feedbacks. In this way, water becomes more than a component of the planet. It becomes a connective tissue, not a controller, not a designer, but a regulator whose influence emerges from motion, interaction, and time. The planet does not hold water still. Water moves through the planet, and in that movement it quietly helps determine how the planet evolves. Water's relationship with life is often described as obvious. Life needs water. Life occurs in water. Life is mostly water. But that familiarity can hide a deeper truth. Water does not instruct chemistry to become biological. It does not guide reactions toward life. It does something quieter and arguably more important. It creates conditions in which chemistry can explore a vast range of possibilities without immediately collapsing into dead ends. In that sense, water enables chemical diversity without directing it. This distinction matters when thinking about how life began. Early ideas about the origin of life often imagined a straightforward progression. Simple molecules form. They combine into more complex ones. Eventually something living appears. Water, in these stories, serves as a background medium where reactions conveniently occur. Alexander Oparin challenged that simplicity in the early 20th century. He proposed that life emerged through a long period of chemical evolution, during which increasingly complex molecules accumulated and interacted in aqueous environments. Water, in his view, was not merely a container. It was the environment that allowed complexity to persist long enough to matter. Oparin emphasized that early Earth was chemically rich and physically dynamic. Energy flowed through the system from sunlight, geothermal heat, and chemical gradients. Water connected these energy sources to reactive molecules, allowing them to mix, collide, and reorganize. Crucially, water did not favor any particular outcome. In an aqueous environment, countless reactions can occur simultaneously. Some products are stable, others fall apart. Many pathways are explored and abandoned. Water allows this exploration by moderating energy, dissolving reactants, and transporting products. This open-endedness is essential. If chemistry were too constrained, only a narrow set of reactions would be possible. If it were too chaotic, complex molecules would be destroyed as quickly as they formed. Water occupies a middle ground. It supports reactions while buffering extremes. One way it does this is through solvation. When a molecule dissolves in water, it becomes surrounded by a shell of oriented water molecules. This solvation stabilizes charged and polar species, lowering energy barriers and allowing reactions to proceed that would be difficult in dry environments. At the same time, water discourages certain arrangements. Nonpolar molecules tend to cluster together, not because they attract one another strongly, but because water reorganizes itself to minimize disruption. This indirect effect shapes molecular assembly without prescribing structure. The result is a chemically permissive environment. Modern research into prebiotic chemistry has expanded this view. Experiments simulating early Earth conditions show that water supports a wide variety of reaction networks. Sugars, amino acids, nucleotides, and simple lipids can all form under plausible conditions. None of these molecules guarantees life, but together they create a chemical landscape rich with possibility. Hydrothermal vent research has added further nuance. Deep beneath the oceans, where seawater interacts with hot rock, steep chemical gradients arise. Alkaline hydrothermal vents, in particular, produce natural proton gradients across mineral membranes. These gradients resemble those used by modern cells to drive metabolism. Water is essential here as well. It transports dissolved gases, moderates temperature, and participates directly in chemical reactions at mineral surfaces. It allows gradients to exist without immediately equalizing them. These environments are far from equilibrium. Energy flows continuously. Matter cycles through multiple states. Water provides the medium that keeps these processes stable enough to persist. What is striking is that even in these focused settings, water does not push chemistry toward a single outcome. Different vent systems produce different chemical mixtures. Slight changes in temperature, composition, or flow lead to divergent results. This introduces the concept of contingency. Contingency means that outcomes depend on specific histories and conditions, not just universal laws. In a contingent system, many futures are possible. The one that occurs is shaped by chance interactions and local constraints. Water supports contingency by allowing chemistry to remain flexible. Because it does not rigidly fix molecular arrangements, water allows multiple pathways to coexist. Molecules can assemble, disassemble, and reassemble in new ways. Structures can form temporarily, break apart, and form again differently. This stands in contrast to environments where chemistry is tightly constrained, such as solid surfaces or highly viscous media. There, once a structure forms, it may be locked in place. Exploration slows. In water, exploration continues. This does not mean that life was inevitable. On the contrary, the very openness of aqueous chemistry suggests that life was one of many possible outcomes. Water provided opportunity, not destiny. Once biological systems did begin to emerge, water's role shifted subtly. It continued to enable diversity, but biological processes introduce specificity. Proteins fold into precise shapes. Nucleic acids store information. Membranes form controlled boundaries. These structures depend on water's properties, but they impose constraints that chemistry alone does not. Even here, water remains a partner rather than a commander. Protein folding, for example, is guided by the hydrophobic effect, where non-polar regions are shielded from water while polar regions remain exposed. Water drives the process energetically, but it does not encode the final structure. The sequence of the protein determines the outcome. Similarly, enzymatic reactions rely on water to stabilize charges and facilitate proton transfer. Yet the specificity of the reaction comes from the enzyme's structure, not from water itself. In this way, water supports biological specificity without defining it. This distinction is easy to miss because water is so deeply integrated into living systems. Cells are mostly water. Metabolism occurs in aqueous solution. Signals propagate through ionic movement in water. But life is not simply chemistry in water. It is chemistry that has learned to exploit water's permissive nature while imposing its own constraints. The transition from prebiotic chemistry to biology marks a narrowing of possibilities. Many reaction pathways are closed off, others are reinforced. Feedback mechanisms appear that preserve successful arrangements. Water remains the medium in which all of this occurs, but it no longer sets the rules. It provides the stage and the conditions, not the script. Understanding this helps avoid a common misconception. Water did not make life happen by itself, nor did life arise in spite of water. Life emerged within a chemical environment that was flexible enough to explore complexity and stable enough to preserve it. That balance is rare. On planets where liquid water is absent, chemistry tends to be either frozen in place or driven too violently by energy. On planets where water is abundant but transient, chemical networks may never persist long enough to evolve. Earth's long-lived oceans provided continuity. They allowed chemical experiments to run for hundreds of millions of years without interruption. Over that time, rare combinations could accumulate and interact. Once biological systems emerged, water became inseparable from them. But the openness that made their emergence possible never disappeared entirely. Even today, water continues to allow variation, mutation, and adaptation. It supports change without enforcing direction. It stabilizes reactions without dictating outcomes. This is perhaps water's most understated contribution to life. It does not choose winners, it keeps the game running. From prebiotic mixtures to living cells, water enables chemistry to explore, refine, and specialize without ever fully closing the door on possibility. And in that quiet permissiveness lies the foundation for biological complexity. Proteins look solid and deliberate when drawn in textbooks. They appear as tidy ribbons folded into precise shapes, each one seemingly engineered for a specific task. This visual impression suggests intention and rigidity, as though a protein simply snaps into its final form and stays there. The reality is far more fluid. A protein is a chain of amino acids, sometimes hundreds long, linked together in a specific sequence. On its own, that chain has no obvious shape. It bends, twists, and flops in countless ways. If left entirely to chance, the number of possible configurations would be astronomically large. Exploring them all would take longer than the age of the universe. And yet, inside living cells, many proteins fold reliably in seconds. This apparent contradiction was highlighted in the 1950s by Cyrus Levinthal, but an even deeper puzzle had already been noted earlier by Walter Kauzmann. Kauzmann focused on what became known as the hydrophobic effect, the tendency of nonpolar parts of molecules to avoid contact with water. At first glance, this seems straightforward. Oil and water separate. Non-polar regions cluster together. But Kauzmann noticed something odd. The driving force behind this clustering was not simply attraction between non-polar groups. Instead, it appeared to arise from water's behavior. This became known as the hydrophobic paradox. Non-polar amino acid side chains do not strongly attract one another. What actually happens is that water organizes itself awkwardly around them. When non-polar groups are exposed, surrounding water molecules lose some of their freedom to form hydrogen bonds. This costs energy. When those groups come together and hide from water, the surrounding liquid becomes freer to reorganize. The system as a whole becomes more stable. The folding of proteins, then, is not driven directly by the protein alone. It is driven by water's preference to maintain its own hydrogen bonding network. This is indirect causation. The protein does not fold because its parts are pulling together strongly. It folds because water pushes certain arrangements away and favors others. The solvent shapes the outcome without specifying it. Understanding this shifts how protein folding is described. Rather than imagining a single path leading to a final structure, scientists now think in terms of energy landscapes. An energy landscape is a way of visualizing all possible configurations of a system and their associated energies. High energy states are unstable and rarely occupied. Low energy states are more stable and more likely. For proteins in water, the landscape resembles a rugged funnel. Many configurations exist at higher energies. As folding proceeds, the chain moves downhill, guided by interactions with water and with itself. There may be local valleys where the protein pauses or misfolds, but the overall slope leads toward a stable form. Importantly, this landscape is shaped by the surrounding water. Change the solvent, and the landscape changes. Proteins that fold easily in water may not fold at all in other liquids. Some may adopt entirely different shapes. The folding problem cannot be separated from the medium in which it occurs. This is why attempts to understand proteins in isolation often fail. In vacuum, proteins behave very differently. Their charged groups interact too strongly. Structures collapse or distort. The balance provided by water disappears. Water screens electrical charges, moderates attractions, and penalizes exposure of nonpolar surfaces. It creates a set of constraints that guide folding without micromanaging it. This guidance is subtle. No single hydrogen bond between water and protein determines the final shape. Instead, millions of fleeting interactions collectively bias the system towards certain configurations. Once folded, proteins are not rigid objects. They breathe. Side chains wiggle. Domains shift. Even the most stable structures fluctuate. These motions are not noise. They are essential for function. Enzymes, for example, rely on flexibility to bind substrates and release products. Structural proteins must absorb stress without breaking. Signaling proteins often switch between multiple shapes depending on their environment. Water participates in all of this motion. It fills cavities, stabilizes transient charges, and absorbs energy from conformational changes. Without water, the delicate balance between stability and flexibility would be lost. This highlights another important point. Protein folding is not about finding a single perfect shape. It is about finding a family of shapes that are stable enough to persist and flexible enough to function. Water supports this balance. The hydrophobic effect ensures that nonpolar regions are generally buried, but not locked away permanently. Hydrogen bonding with water stabilizes polar regions while allowing them to rearrange. Electrostatic screening prevents charges from dominating the structure. Together, these influences create a system that is robust without being brittle. This robustness underlies biological complexity. Living systems depend on large numbers of proteins interacting in crowded, noisy environments. Mistakes happen. Conditions change. Temperatures fluctuate. Chemical concentrations vary. Despite this, biological function persists. Water plays a central role in this resilience. It cushions interactions. It absorbs disturbances. It allows systems to explore small variations without catastrophic failure. Even misfolding, often seen as a problem, reflects this flexibility. Proteins can adopt alternative structures under stress. Some misfolded states are reversible. Others are managed by cellular machinery. The system adapts. From a purely chemical standpoint, none of this is obvious. A long chain of amino acids should behave unpredictably. That it does not is a consequence of indirect causation mediated by water. This perspective also explains why protein design is difficult. Knowing the sequence is not enough. The environment matters. Solvent conditions, temperature, ionic strength, and crowding all influence the energy landscape. Biological specificity emerges not from rigid instruction, but from constraint and bias. Water constrains what is unfavourable. It biases what is likely. It leaves room for variation. This is a powerful recipe for complexity. At a deeper level, protein folding illustrates a general principle. Complex biological behaviour often arises not because components actively enforce order, but because the environment makes some arrangements easier than others. Water does not tell proteins how to fold. It makes certain foldings energetically comfortable. This distinction becomes increasingly important as systems grow larger. Networks of proteins interact, assemble, and disassemble. Pathways overlap. Feedback loops appear. Stability emerges from countless small interactions, most of them mediated by water. In this sense, water is not just the medium of life. It is part of the mechanism by which biological order arises and persists. The folding of proteins is one of the clearest examples of this partnership. A simple chain becomes a functional machine, not through direct instruction, but through a landscape shaped by an ever-present solvent. Indirect causation, guided by water, scales upward into biological complexity. What begins as an avoidance of awkward interactions between water and nonpolar groups becomes a foundation for structure, function, and life itself. And once again, water achieves this not by imposing design, but by quietly shaping possibility. Inside a living cell, water is everywhere, but it is not all the same. A cell is not a glass of liquid. It is a crowded, structured environment packed with proteins, membranes, nucleic acids, and molecular machines. Roughly speaking, water still makes up most of the cell by mass, but much of it is confined, influenced, or altered by nearby surfaces. This immediately raises a question. Does water inside cells behave like ordinary liquid water, or does it take on different properties? The safest answer is careful and qualified. Some aspects of intracellular water are well established. Other claims remain contested. The difficulty lies not in the curiosity of the question, but in how hard it is to measure water at this scale without disturbing it. One of the most widely discussed ideas in this area comes from Gerald Pollack, who has proposed the existence of what he calls exclusion zone water. According to this idea, water adjacent to certain hydrophilic surfaces forms a region that excludes solutes, carries different electrical properties, and may adopt a more ordered structure than bulk liquid water. Laboratory experiments have shown that near some surfaces, particularly charged or polar ones, dissolved particles are pushed away over distances larger than expected. These regions can extend for tens or even hundreds of micrometers under certain conditions, far larger than the immediate molecular layer typically considered in surface chemistry. This observation is real and reproducible in some experimental setups. Water near surfaces does behave differently from water far away. Molecules close to membranes, proteins, or mineral interfaces often show altered orientation, slower movement, and modified hydrogen bonding patterns. Where the debate begins is in how these findings are interpreted. One interpretation suggests that exclusion zone water represents a distinct phase of water, fundamentally different from liquid water as usually understood. This is where many researchers urge caution. While structured layers of water near surfaces are well known, extending this idea to a new bulk phase inside cells remains controversial. Most physical chemists and biophysicists agree on a narrower point. Water near interfaces is structured. Its properties differ from bulk water. Hydrogen bonds may be more ordered. Molecular motion may be restricted. Electrical behavior can be altered. What is less clear is how far these effects extend, how stable they are under physiological conditions, and how dominant they are in living cells. Cells are dynamic. Proteins move, membranes flex, ions flow. Water is constantly being displaced, reorganized, and exchanged. Any structured region must exist within this restless environment. Experimental ambiguity is unavoidable here. Measuring water structure often relies on indirect methods. Techniques such as nuclear magnetic resonance, infrared spectroscopy, and neutron scattering provide averages over many molecules and timescales. They can detect changes in mobility or bonding, but interpreting those changes requires models. Different models can fit the same data. For example, slower water motion near a surface could indicate a distinct ordered phase. It could also reflect simple crowding effects or transient binding to nearby molecules. Distinguishing between these possibilities is challenging. This is not a failure of experimentation. It is a limitation imposed by scale. Inside a cell, water molecules interact with surfaces every few nanometers. There is very little space where water behaves as it would in a beaker. In that sense, intracellular water is almost always interfacial. This makes the idea of structured water near surfaces unsurprising. What matters is degree, not existence. Another important distinction lies between structural influence and functional significance. Even if water near surfaces is partially ordered, the question remains whether this ordering plays a major role in cellular processes, or whether it is simply a background condition that cells have adapted to. Some hypotheses suggest that structured water could influence protein folding, enzyme activity, or ion transport. These ideas are intriguing, but evidence remains mixed. In many cases, observed effects can be explained using conventional electrostatics, hydration shells, and crowding models without invoking a new water phase. That does not make the questions unimportant. It highlights the need for precision. One reason these discussions attract attention is that water inside cells challenges simple assumptions. Textbook descriptions often imply that cellular chemistry occurs in dilute aqueous solution. In reality, cells are densely packed. The effective concentration of macromolecules is high. Free water is limited. This crowding alters reaction rates, diffusion, and molecular interactions. Water mediates all of it. Near membranes, water molecules align with charged head groups. Near proteins, they form hydration shells that stabilize structure and facilitate motion. Near nucleic acids, they help screen charges along the backbone. These effects are well supported experimentally. Where interpretation becomes speculative is when local ordering is assumed to propagate over large distances or to dominate cellular behavior. Most evidence suggests that structured water regions are local, transient, and sensitive to conditions. Temperature, ionic strength, and molecular composition all matter. Change them, and water's behavior shifts. This sensitivity complicates attempts to generalize. It also explains why results can vary between laboratories. Small differences in surface preparation, purity, or measurement technique can lead to different observations. What appears as a stable exclusion zone in one setup may shrink or vanish in another. Scientific caution is warranted here. None of this diminishes the importance of studying water inside cells. On the contrary, it underscores how central water is to cellular function. It is not just the solvent in which life occurs. It is an active participant whose behavior is shaped by the crowded, structured environment of the cell. The challenge lies in describing the participation accurately. At present, the most defensible position is this: water inside cells is heterogeneous. Its properties vary depending on proximity to surfaces, local charge distributions and molecular crowding. Some degree of structuring near interfaces is real and measurable. Claims of large-scale, long-lived alternative phases remain unproven. This careful distinction is essential for progress. It keeps attention focused on what can be tested and refined. It avoids overextending interpretation beyond evidence. It encourages better experiments rather than broader claims. As measurement techniques improve, this picture will likely sharpen. Faster spectroscopic methods, higher resolution imaging, and more sophisticated simulations are already revealing new details about how water behaves in complex environments. What remains constant is the difficulty of the task. Water inside cells cannot be isolated without changing it. Probing it risks disturbing it. Observations are always indirect. This makes cellular water one of the most challenging subjects in biophysics. It sits at the boundary between chemistry, physics, and biology, resisting clean categorization. In this way, it mirrors the broader theme running through water science: familiar, essential, and everywhere, yet stubbornly difficult to pin down in full detail. Understanding water inside cells requires not only better tools, but better questions. It demands clarity about what is known, what is inferred, and what remains speculative. That demand naturally leads toward the next challenge. If water is this difficult to characterize in one of the most intensively studied environments in science, how reliable are the methods used to study it more generally? The problem of water inside cells does not end with biology. It exposes the limits of measurement itself. Trying to measure water is like trying to photograph a crowd while everyone is constantly changing places. By the time an image is captured, the moment has already passed. At the molecular level, water is never still. Hydrogen bonds form and break in trillionths of a second. Molecules rotate, vibrate, and translate continuously. Local structures appear and dissolve faster than most instruments can track. Any attempt to observe water risks averaging away the very behavior that makes it interesting. For much of scientific history, this limitation was invisible. Early measurement techniques focused on static properties: density, boiling point, heat capacity, and compressibility could all be measured reliably. These quantities are averages, and averages hide motion. As understanding deepened, it became clear that water's defining features lie not in static structure, but in dynamics. The challenge shifted from locating molecules in space to tracking how they move in time. This is where temporal resolution becomes as important as spatial resolution. Knowing where atoms are is useful. Knowing how long they stay there can be decisive. Many traditional techniques provide excellent spatial detail but blur time. X-ray diffraction, for example, excels at revealing ordered structures in crystals. Liquid water does not crystallize, and even when short-range order exists, it fluctuates too quickly to be captured cleanly. What appears instead is a time-averaged picture, smoothed over countless rearrangements. Spectroscopic methods offer another route. By probing how water absorbs and emits light at specific frequencies, scientists can infer information about molecular motion and bonding. Infrared spectroscopy, Raman spectroscopy, and nuclear magnetic resonance all provide valuable insights. But here again, interpretation depends on timescale. A signal that appears stable may actually be the average of rapid fluctuations. Without knowing how fast those fluctuations occur, it is easy to mistake motion for structure. The importance of time was brought into sharp focus by Ahmed Zewail, whose work in the late 20th century helped establish the field of femtochemistry. Zewail developed techniques using ultra-fast laser pulses to observe chemical reactions as they happen, on timescales of femtoseconds, A femtosecond is a millionth of a billionth of a second. At these timescales, atoms can be seen moving. Bonds can be observed forming and breaking. Transient states that were once purely theoretical become measurable. Applied to water, ultrafast spectroscopy reveals a world in constant flux. Hydrogen bonds stretch and collapse within a few hundred femtoseconds. Vibrational energy flows through the network almost immediately. Local arrangements flicker in and out of existence. These observations confirm what theory suggested. Liquid water is not a static assembly of molecules arranged in a preferred geometry. It is a dynamically reorganizing system whose properties emerge from motion. Yet even ultra-fast techniques come with limits. To observe something, it must be perturbed. A laser pulse deposits energy. That energy alters the system, however briefly. The measurement itself becomes part of the process. Careful experimental design can minimize disturbance, but it cannot eliminate it. This introduces an observer limitation that is especially pronounced for water. Because water is so responsive, even small perturbations can alter its behavior. Heating, electric fields, confinement, and surface interactions all shift hydrogen bonding patterns. The act of measurement risks changing what is being measured. This does not make observation meaningless. It means that results must be interpreted with humility. Different techniques emphasize different aspects of water's behavior. Neutron scattering is sensitive to hydrogen positions but averages over time. Infrared spectroscopy captures vibrational dynamics, but requires careful modeling to translate signals into structure. Nuclear magnetic resonance provides information about mobility and environment, but often lacks spatial specificity. Each method offers a partial view. Combining techniques helps, but it also introduces complexity. Data from different experiments must be reconciled. Models are required to bridge gaps. Assumptions creep in. This is where the moving target becomes a modeling problem. Experimental measurements produce signals. Those signals must be translated into molecular descriptions. This translation relies on theoretical frameworks and computational models. If the models are incomplete or biased, interpretation follows suit. For water, this is a persistent challenge. Models that reproduce bulk properties may fail at interfaces. Models that capture hydrogen bonding accurately may struggle with long-range correlations. Some emphasize electronic structure. Others prioritize efficiency over detail. No single model captures everything. Temporal resolution complicates matters further. A model that matches average behavior may miss transient structures that matter for specific processes. Conversely, a model that reproduces ultra-fast dynamics may be computationally impractical for large systems. The result is a patchwork understanding. This does not reflect negligence or lack of effort. Water is one of the most intensively studied substances in science. It reflects the inherent difficulty of describing a system whose defining features are collective, dynamic, and sensitive. Even defining what counts as structure becomes tricky. Is a hydrogen bond meaningful if it lasts only a fraction of a picosecond? Does a network exist if its members are constantly changing? These are not semantic questions. They influence how measurements are interpreted. Observer limitations extend beyond instruments. Human intuition also struggles with rapidly fluctuating systems. It is tempting to imagine water as a static arrangement, with occasional motion layered on top. In reality, motion is the arrangement. This inversion challenges common mental models. When a scientist reports a structure in liquid water, it often refers to a statistical preference rather than a fixed entity. Peaks in distribution functions, correlation lengths, and average orientations describe tendencies, not objects. Without careful explanation, these distinctions can blur. The consequence is that water can appear contradictory. One experiment suggests order, another suggests disorder. Both may be correct within their respective windows of time and space. Understanding water requires accepting that no single snapshot tells the full story. Temporal resolution determines which aspects are visible. Spatial resolution determines how localized those aspects appear. Observer influence shapes what survives measurement. Together, these factors define the limits of knowledge. This is not unique to water, but water amplifies the issue because its behavior is so fast and so cooperative. There is no stable reference frame at the molecular level. Everything moves relative to everything else. As techniques continue to improve, new details emerge. Ultrafast spectroscopy reveals fleeting states. Improved scattering methods resolve subtler correlations. Advances in computation allow longer and more accurate simulations, but each improvement also exposes new layers of complexity. The moving target does not settle, it becomes more detailed. This has important implications for how models are constructed and trusted. A model is always an approximation. For water, the question is not whether a model is correct in absolute terms, but which aspects it captures well and which it smooths over. Recognizing this helps prevent overconfidence. It encourages careful comparison between experiment and theory. It keeps attention focused on uncertainty rather than closure. Water, measured with ever greater precision, continues to resist being frozen into a final description. And that resistance is not a failure of measurement, it is a feature of the system being measured. When experiments struggle to keep up with motion, scientists turn to simulation. If water cannot be held still long enough to be measured cleanly, perhaps it can be recreated inside a computer. Perhaps its behavior can be calculated step by step, molecule by molecule, interaction by interaction. This idea has driven decades of work in molecular modeling, and it has produced remarkable progress, along with persistent disagreement. At the heart of most simulations of liquid water lies molecular dynamics. In this approach, atoms are treated as particles that move according to forces acting between them. Positions and velocities are updated repeatedly over very small time steps, allowing the system to evolve. The success of this method depends entirely on how those forces are described. These descriptions are known as force fields. A force field specifies how strongly atoms attract or repel one another, how bonds stretch and bend, and how charges interact. For water, this includes parameters for bond lengths, angles, partial charges, and hydrogen bonding behavior. Force fields are not derived directly from first principles, they are constructed. Most are empirical or semi-empirical. Their parameters are chosen to reproduce certain known properties such as density, diffusion rate, heat capacity, or dielectric behavior. If a model reproduces these targets well, it is considered successful. But this success is selective. A force field tuned to match bulk properties may fail at interfaces. One optimized for room temperature behavior may perform poorly under extreme pressure. Some reproduce structure well but get dynamics wrong. Others capture dynamics but distort thermodynamics. This is not a flaw in execution. It reflects the fact that no finite set of parameters can capture all aspects of a system as complex and responsive as water. As a result, different force fields disagree. Simulations using different models can predict different hydrogen bond lifetimes, different degrees of a local order, and different responses to temperature and pressure. All may appear reasonable. All may reproduce some experimental data, yet they do not converge on a single picture. This has led to long-standing debates within the field. One axis of disagreement lies between empirical modelling and approaches that attempt to derive interactions from quantum mechanics more directly. These latter approaches are often grouped under the term ab initio modelling, meaning calculations based on fundamental principles rather than fitted parameters. Density functional theory plays a central role here. It is a quantum mechanical method that describes how electrons are distributed within a system. In principle, it allows interactions to be calculated from electronic structure rather than imposed by parameter choice. In practice, density functional theory introduces its own approximations. The exact mathematical form of electron interaction is not known, so it must be approximated using functionals. Different functionals emphasize different aspects of behavior. Some handle hydrogen bonding well, others struggle with dispersion forces. No single choice is universally correct. Ab initio simulations are also computationally expensive. Simulating large volumes of water for long times remains difficult. As a result, these methods often trade scale for detail. This creates tension. Empirical force fields can simulate millions of molecules over long times, but rely on assumptions built into their parameters. Ab initio methods capture electronic effects more faithfully, but at the cost of system size and duration. Neither approach can claim complete authority. What complicates matters further is that models are often judged by how well they reproduce experimental observables. But as already seen, experiments themselves depend on interpretation and averaging. A model may match one experiment while contradicting another. This raises a subtle but important point. Agreement with data does not guarantee correctness of mechanism. Two models can reproduce the same average behavior for different reasons. One may rely on overly rigid hydrogen bonds. Another may allow more fluctuation but compensate elsewhere. Without direct access to the underlying motion, it can be difficult to decide which representation is closer to reality. This is where assumptions quietly accumulate. Every model encodes choices about what matters and what can be ignored. Should hydrogen atoms be treated explicitly or averaged? Should polarization be fixed or allowed to respond dynamically? Should quantum effects such as nuclear motion be included or approximated classically? None of these decisions is neutral. They reflect judgments about scale, relevance, and feasibility. They shape outcomes in ways that are not always obvious. When different groups make different choices, disagreement follows. These disagreements are not signs of confusion. They are signs that water sits near the limits of current modelling approaches. Unlike a rigid solid or a dilute gas, liquid water occupies a regime where interactions are strong enough to matter, but weak enough to fluctuate. Collective behaviour emerges from many small effects. Capturing this accurately requires balancing detail and tractability. As computational power has increased, models have grown more sophisticated. Polarizable force fields allow charges to respond to their environment. Machine learning approaches attempt to infer interaction patterns from large data sets. Hybrid methods combine quantum and classical descriptions. Each advance improves some aspects while introducing new questions. For example, adding polarization improves dielectric behavior, but increases computational cost and parameter complexity. Machine-learned potentials can reproduce training data impressively, but may extrapolate poorly outside it. Hybrid methods require careful coupling between levels of description. No approach escapes trade-offs. This leads naturally to philosophical implications about what models are meant to do. Are they intended to be literal representations of reality, or practical tools that reproduce selected behaviors? Should a model that predicts observables accurately be preferred even if its internal picture seems artificial? Or should physical plausibility take precedence over numerical agreement? There is no single answer. In water science, models often serve as hypotheses. They propose a way the system might behave, constrained by known principles and data. Experiments then test consequences. Disagreement becomes productive rather than problematic. Seen this way, modelling water is less about convergence on a final description, and more about mapping a space of possibilities. Each model highlights certain mechanisms and downplays others. Together, they build a composite understanding. This perspective helps explain why debate persists even after decades of work. Water does not yield easily to a single framework. Its behaviour spans quantum and classical regimes. It is sensitive to context and scale. It resists reduction to a minimal set of rules. Models reflect this resistance. They encode assumptions because assumptions are unavoidable. They simplify because simplification is necessary. They disagree because different simplifications emphasize different truths. Recognizing this does not weaken confidence in science. It clarifies its scope. Models are not mirrors, they are lenses. Each brings certain features into focus while blurring others. For a substance as intricate as water, no single lens captures everything. This realization invites humility. It also invites creativity. By comparing models, by testing where they succeed and fail, scientists learn not only about water, but about the limits of representation itself. They learn how collective behavior challenges reductionist thinking. They learn where intuition breaks down. Water becomes a case study in how knowledge is constructed, not as a finished picture, but as an evolving set of approximations, each grounded in evidence, each open to revision. As simulations grow more detailed and experiments more precise, disagreement does not vanish. It becomes more nuanced. And through that nuance, a deeper understanding slowly takes shape. Liquid water occupies an unusual position in physics. It is everywhere, endlessly useful, and studied in extraordinary detail. And yet, within condensed matter physics, it remains one of the clearest examples of a problem that refuses to close. Solids are well understood because their atoms occupy fixed positions and vibrate around them. Gases are tractable because their particles interact weakly and briefly. Both extremes allow clean theoretical descriptions. Liquids sit between them, sharing features of both without fully belonging to either. Atoms in a liquid are close together, like a solid but constantly rearranging like a gas. Interactions are strong enough to matter, yet transient enough to evade simple treatment. This intermediate character makes liquids difficult to generalize. Among all liquids, water stands out as especially resistant to simplification. Condensed matter physics has produced powerful theories for crystals, magnets, superconductors, and phase transitions. Many of these rely on symmetry, order parameters, and long-lived structures. Liquid water provides none of these in stable form. Its order is local and fleeting. Its correlations fluctuate. Its structure is statistical rather than geometric. Philip Ball has explored this tension extensively, not as a popular mystery, but as a scientific reality. His synthesis of decades of research emphasizes that water's difficulty is not exaggerated. It genuinely sits at the edge of what current theoretical frameworks handle well. One reason for this is that liquids lack a unifying theory. For solids, lattice models provide a common language. For gases, kinetic theory offers a statistical framework. For liquids, no equivalent universal description exists. Each liquid must often be treated on its own terms, using approximations tailored to its interactions. Water complicates this further by combining several competing tendencies. Hydrogen bonding promotes local order. Thermal motion disrupts it. Electrostatic interactions extend over longer ranges. Molecular geometry enforces directional constraints. None of these dominates completely. The system balances on the edge between structure and disorder. This balance produces intermediate states. At any given moment, regions of liquid water resemble ice. Elsewhere, they resemble a disordered fluid. Between these extremes lies a continuous spectrum of configurations. No sharp boundary separates one from another. The liquid samples them all. These intermediate states matter because they influence measurable properties. Density anomalies, compressibility, heat capacity, and response to pressure all depend on how populations of local structures shift with conditions. The difficulty lies in describing these shifts rigorously. In a crystal, phase transitions involve clear changes in symmetry. In a gas, changes are smooth and predictable. In liquid water, transitions are blurred. Structural motifs fade in and out rather than appearing or disappearing. This makes it hard to define what the relevant degrees of freedom even are. Should water be described in terms of individual molecules, hydrogen bond networks, clusters, or density fluctuations? Each description captures something real. None captures everything. Experimental evidence supports this ambiguity. Scattering experiments reveal short-range order, but no repeating pattern. Spectroscopy shows distinct vibrational modes, but heavily broadened by motion. Thermodynamic measurements reveal anomalies, but do not specify their microscopic origin uniquely. As a result, multiple interpretations coexist. Some models emphasize the role of the local tetrahedral order inherited from ice. Others highlight density fluctuations resembling those near critical points. Some propose that water contains two interconverting liquid-like states at low temperatures. Others argue that such distinctions are unnecessary. Each view is supported by some evidence and challenged by other data. This situation would be uncomfortable if water were an obscure material. It is not. It is the reference liquid against which others are compared. That fact sharpens the problem. Condensed matter physics often relies on simplification. It seeks minimal models that capture essential behavior. Water resists reduction to a minimal set. Remove hydrogen bonding, and anomalies vanish. Remove electrostatics, and structure dissolves. Remove motion, and the liquid freezes. What remains is not water. This resistance has philosophical implications. It challenges the idea that understanding necessarily converges on a single, elegant description. It suggests that some systems may require layered explanations, each valid within its own domain. Liquid water appears to be such a system. Its behavior emerges from interactions that are individually simple, but collectively intricate. No single interaction explains its properties. No single scale dominates. This places water squarely in the category of frontier problems, not because it is mysterious in a dramatic sense, but because it sits at the boundary of existing theory. Condensed matter physics excels at equilibrium states and long-lived order. Liquid water is neither fully equilibrated nor ordered in that way. It exists in a state of continual reorganization, stabilized by motion itself. Understanding such systems may require new conceptual tools. Already ideas from complexity science, statistical field theory, and non-equilibrium thermodynamics are being applied. Correlation functions replace structures. Distributions replace configurations. Dynamics take precedence over geometry. Even so, progress is incremental. No experiment delivers a decisive picture. No simulation settles debate. Each adds detail, sharpens constraints, and reveals new questions. This is not stagnation. It is the normal pace of frontier science. Water's status as an unsolved problem does not mean it is poorly understood in practical terms. Engineers use it reliably. Biologists depend on it. Climate models incorporate its behavior with considerable success. The unresolved questions lie deeper. They concern why water's anomalies cluster together, how local order propagates, and whether its behavior can be unified within a broader theoretical framework for liquids. They concern whether the intermediate states that dominate water can be described cleanly, or whether they are inherently context-dependent. These questions matter beyond water. If liquid water resists universal theory, other complex fluids likely do as well. Understanding water may illuminate why some systems defy reduction more generally. In this way, water becomes a test case, a familiar substance that exposes the limits of current approaches. Philip Ball has argued that this should not be seen as a failure, but as an invitation to rethink what counts as explanation, and how theories should be structured when systems are neither simple nor ordered. Liquid water, despite its ordinariness, occupies this challenging middle ground. It is not chaotic enough to ignore. It is not ordered enough to solve. It lives in between, where patterns are temporary, correlations are statistical, and structure is always on the verge of change. That intermediate nature is precisely what makes it so difficult to capture in a single theory. And it is why, even after centuries of study, liquid water remains one of the most instructive unsolved problems in physics. After centuries of measurement, modeling, and experimentation, it is reasonable to ask why water still resists a settled explanation. The question is not rhetorical. Many scientific problems do converge. As tools improve and data accumulates, uncertainty narrows. Competing theories fall away. Consensus forms. Water has not followed that path in the way one might expect. One reason lies in the nature of complexity itself. Complexity theory studies systems made up of many interacting components, whose collective behavior cannot be predicted simply by analyzing each part in isolation. These systems are often non-linear, meaning that small changes can produce disproportionately large effects, and cause and effect are not neatly proportional. Liquid water fits this description remarkably well. Each molecule follows simple physical laws. The interactions between pairs of molecules are well characterized, and yet, when trillions of them interact simultaneously, the resulting behavior is not a straightforward sum of those interactions. This is a hallmark of nonlinear systems. In linear systems, knowing the parts is enough. Double the input and the output doubles. In nonlinear systems, doubling the input can leave the output unchanged, amplify it, or invert it entirely depending on context. Water behaves this way across many properties. Small temperature changes near freezing produce expansion instead of contraction. Minor shifts in pressure produce new structural motifs. Slight variations in composition alter large-scale behavior. Murray Gell-Mann explored such phenomena through the lens of complex adaptive systems, while his work spanned physics, biology, and information theory. The central idea applies here. In complex systems, patterns emerge from interaction, feedback, and adaptation rather than from centralized control or simple rules. Water is not adaptive in a biological sense, but its hydrogen bond network continuously responds to local conditions. Bonds form where they are energetically favorable and dissolve where they are not. Patterns adjust dynamically. The system reorganizes without instruction. This responsiveness makes reductionism stall. Reductionism has been extraordinarily successful in science. Breaking systems down into components has revealed atomic structure molecular bonding, genetic coding, and much more. But reductionism assumes that understanding the smallest parts will eventually explain the whole. With water, that assumption reaches a limit. Knowing everything about an isolated water molecule does not explain the properties of liquid water. Knowing everything about a pair of molecules does not explain the network. Even knowing a great deal about local clusters does not fully determine large-scale behavior. Each level introduces new interactions. This does not mean reductionism is wrong. It means it is incomplete when used alone. Water demands a complementary approach that focuses on collective behavior and interaction across scales. One way to see this is to ask a simple question. At what scale does water become water? Is it at the level of individual molecules? Those behave very differently in isolation. Is it at the level of hydrogen-bonded pairs? Those are fleeting. Is it at the level of clusters? Those constantly rearrange. There's no single scale where water's defining properties suddenly appear. They emerge gradually across a continuum. This lack of a privileged scale is unusual. Many systems have a clear level at which their behavior stabilizes. In crystals, it is the lattice. In gases, it is the statistical ensemble. In living organisms, it is often the cell. Liquid water has no such anchor. Its properties depend on correlations that extend over multiple scales simultaneously. Local hydrogen bonding influences intermediate range structure, which influences macroscopic properties such as density and heat capacity. None of these levels can be ignored. None dominates completely. This scale-free character complicates theory. Models must choose which scales to emphasize local structure, and long-range correlations may be missed. Emphasize bulk averages, and subtle structural motifs vanish. Emphasize dynamics, and thermodynamic consistency may suffer. Each choice captures part of the truth and obscures another. This is why decades of study have produced refinement rather than closure. As tools improve, water appears more intricate, not less. New experimental techniques reveal finer temporal structure. New simulations expose longer-range correlations. Each advance resolves some questions and raises others. From the perspective of complexity theory, this is expected. Complex systems do not yield single, final explanations. They are better understood through multiple, overlapping descriptions, each valid within its domain. This reframes what it means to understand water. Rather than seeking a definitive model that explains everything, scientists increasingly aim to map regimes of behavior. Under these conditions, these approximations work. Under those conditions, others apply. Transitions between regimes become objects of study in their own right. Water becomes a system of context rather than a single object. This also explains why disagreement persists among experts. Different researchers focus on different scales, different phenomena, and different questions. They build models suited to their goals. Those models may not align perfectly because they were never meant to. Disagreement here is not noise, it is information. It signals that water cannot be compressed into a single explanatory frame without loss. It resists being flattened. There is a temptation to see this as a failure to complete the story. In reality, it reflects the maturity of the field. Simple problems are solved early. Difficult ones remain. Water sits at the intersection of many disciplines: physical chemistry, condensed matter physics, statistical mechanics, biophysics, geophysics, and planetary science all approach it from different angles. Each brings useful tools. None has final authority. This interdisciplinary position further slows convergence. Concepts do not always translate cleanly across fields. Terms carry different meanings. Models optimized for one domain may be unsuitable in another. Yet this diversity is also productive. It prevents premature closure. It keeps multiple perspectives alive. At a deeper level, water challenges an assumption that often goes unexamined. The assumption that nature must be describable in simple, unified terms at every scale. Complexity theory suggests otherwise. Some systems may be irreducibly complex in the sense that their behavior cannot be compressed without losing essential features. This does not mean they are unknowable. It means knowledge takes a different form. Instead of a single equation or model, understanding consists of constraints, patterns, tendencies, and limits. It consists of knowing what is possible, what is likely, and what is excluded. Water fits this pattern well. Scientists know a great deal about what water does. They know its anomalies, its phase behavior, its role in life and climate. They can predict many outcomes reliably. What remains unsettled is not water's behavior, but water's unification. Why do so many anomalies cluster together? Why do small changes propagate across scales? Why does the hydrogen bond network generate such resilience and flexibility simultaneously? These questions point toward limits of knowledge rather than gaps easily filled by more data. Limits do not imply ignorance. They define the boundary between what can be simplified and what must be treated as complex. Recognizing these limits is itself a form of understanding. It allows science to proceed without the illusion that every system must yield a tidy summary. It opens space for richer descriptions that respect complexity rather than suppress it. Water, after all, does not behave badly. It behaves consistently with its nature as a densely interacting multiscale system. That nature simply does not lend itself to a single settled account, and perhaps that is the deeper lesson. Some of the most familiar substances reveal the sharpest boundaries of explanation, not because they are exotic, but because they sit precisely where simplicity gives way to complexity. Water has been studied so much not because it is simple, but because it is endlessly revealing. Each layer of understanding exposes another beneath it, and in that unfolding science encounters not failure, but the quiet edges of what it can fully resolve. Push water far enough and it becomes something else entirely. Most everyday experience takes place within a narrow slice of water's possible conditions. Temperatures hover near freezing to boiling. Pressures stay close to that at Earth's surface. Within this familiar window, water behaves strangely enough. Outside it, the strangeness multiplies. As pressure increases, water does not follow a simple path from liquid to solid. Instead, it reveals a branching landscape of phases, each with distinct structures and properties. The phase diagram does not tidy itself under extremes. It becomes more elaborate. This behavior was first hinted at through laboratory experiments that compressed water and ice far beyond everyday conditions. As pressure rises, familiar ice gives way to denser crystalline forms. Molecules rearrange, hydrogen bonds shift, and entirely new lattices appear. Each phase occupies a specific region of temperature and pressure, and transitions between them can be abrupt or gradual depending on conditions. What emerges is not a single extreme form of water, but a family. At sufficiently high pressures and temperatures, another transformation occurs. Water enters a state known as superionic. In this phase, oxygen atoms form a relatively fixed lattice, while hydrogen ions move freely through it, almost as if the material were both solid and liquid at the same time. Superionic water conducts electricity efficiently. Its hydrogen ions behave more like a fluid than part of a crystal, while the oxygen framework remains ordered. This is not a metaphor. It is a distinct physical state predicted by theory and supported by high-pressure experiments and simulations. The conditions required for supersonic water are extreme by Earth standards. Pressures millions of times greater than atmospheric pressure and temperatures of thousands of degrees are involved. These are not conditions found at Earth's surface, they are found elsewhere. Planetary interior research suggests that such states of water may exist deep inside ice giant planets such as Uranus and Neptune. Beneath their visible atmospheres lie layers where water, ammonia, and other volatiles are compressed and heated beyond familiar regimes. In these environments, water may not be a liquid ocean or a solid ice layer. It may be supersonic, contributing to unusual magnetic fields and internal heat transport. This possibility reshapes how water is understood in planetary contexts. It is no longer just a surface condition tied to habitability. It becomes a major structural component of planetary interiors. As pressure increases, hydrogen bonds shorten and reorganize. Molecular identity blurs. Traditional distinctions between solid, liquid, and plasma begin to overlap. Phase boundaries shift and multiply. This is why water's phase diagram grows more complex rather than simpler under extreme conditions. Many substances approach simplicity when pushed hard enough. At very high temperatures, everything becomes gas. At very high pressures, many materials collapse into dense solids. Water refuses this monotony. Instead, it discovers new ways to arrange itself. Each new phase reveals something about the underlying interactions. Hydrogen bonding competes with electrostatics. Molecular geometry contends with compression. Thermal motion disrupts order even as pressure enforces it. These competing influences generate a rich variety of outcomes. Studying water under such extremes is not merely academic curiosity. It provides insight into fundamental physics. Extreme conditions strip away familiar assumptions and expose which interactions truly matter. For example, supersonic behavior highlights the dual nature of hydrogen in water. Light, mobile, and weakly bound, hydrogen responds differently to pressure and temperature than oxygen. This asymmetry becomes pronounced under compression, revealing how mass and bonding shape collective behavior. Experiments recreating these conditions are challenging. Diamond anvil cells squeeze tiny samples to enormous pressures. High-powered lasers deliver intense bursts of energy. Measurements must be taken quickly before samples escape or transform further. Despite these difficulties, results have accumulated. They show that water's adaptability continues far beyond ordinary experience. Its capacity to reorganize persists even when pushed into regimes that challenge experimental control. This adaptability has broader implications. In planetary science, understanding water's high-pressure phases helps explain magnetic field generation, heat flow, and internal structure. The unusual magnetic fields of Uranus and Neptune, tilted and offset from their centers, may be influenced by conductive layers of supersonic water deep within. In astrophysics, water under extreme conditions informs models of exoplanets. Many discovered worlds are larger than Earth, but smaller than gas giants. Their interiors may host vast quantities of water in unfamiliar phases. Habitability, magnetic shielding, and geological activity all depend on how water behaves there. Even beyond planets, extreme water behavior touches on fundamental questions about matter. It challenges simplistic categorizations and forces reconsideration of how phases are defined. Phase diagrams are often taught as tidy maps. For water, they are more like branching trees. New limbs appear as conditions extend. Boundaries blur, states overlap. Rather than converging towards simplicity, the diagram expands. This is a recurring theme. Pushing water to extremes does not eliminate its anomalies, it reveals new ones. The value of these studies lies not only in cataloguing phases, but in understanding principles. Which interactions dominate under compression? How does hydrogen bonding adapt? When does molecular identity persist and when does it dissolve? Extreme conditions act as stress tests for theory. Models that work near ambient conditions may fail under pressure. Assumptions break down. New behaviors emerge that demand explanation. In this way, extremes drive discovery. They show that water's familiar properties are not isolated quirks. They are manifestations of deeper flexibility. The same tendencies that cause ice to float also allow water to adopt superionic forms. The same hydrogen bonds that structure liquid water reorganize under pressure into entirely new architectures. This continuity across conditions is striking. It suggests that water's behavior cannot be understood by focusing solely on the comfortable middle ground. Its full character emerges only when examined across its entire range of possibilities. Extreme studies also provide perspective. They remind us that Earth's oceans occupy a narrow and fortunate niche within water's broader phase space. Liquid water at moderate temperature and pressure is not the default state of the universe. It is one option among many. That realization sharpens questions about water's role elsewhere. If water can exist in so many forms, which ones matter for life, geology, and planetary evolution? Which behaviors are essential and which are incidental? Exploring extremes does not answer these questions directly, it frames them. By revealing how water behaves when pushed far from the familiar, science gains leverage on why its ordinary behavior is so special. Not because it is unique, but because it sits at a crossroads of competing tendencies. Water under extreme conditions is not an oddity, it is a continuation. Each new phase discovered expands understanding rather than closing it. Each extreme reveals another facet of a substance that refuses to be simple. From laboratory compression to planetary interiors, water remains adaptable, intricate, and surprising. And as attention shifts outward, beyond Earth, these discoveries take on broader significance. Water is not just a local substance. It is a cosmic material, shaped by pressure, heat, and time across the universe. Understanding it at its extremes is not a detour from understanding it here. It is part of the same story, unfolding across scales. Water did not originate on Earth. That statement is not philosophical. It is chemical. The hydrogen and oxygen that make up water were forged in different astrophysical settings long before planets existed. Hydrogen emerged in the earliest moments after the universe began. Oxygen formed later, inside stars, released through stellar winds and supernova explosions. Water itself assembled wherever conditions allowed those elements to meet and bind. Understanding where Earth's water came from requires tracing that history backward, not just across space, but across time. Astrochemistry provides the tools for this tracing. It studies how molecules form, survive, and evolve in space, from cold interstellar clouds to young planetary systems. In these environments, water appears early and persistently. Infrared observations reveal water ice coating dust grains in molecular clouds. These grains drift through regions only a few tens of degrees above absolute zero. Even there, water forms efficiently, aided by surface reactions that allow hydrogen atoms to combine with oxygen. This means that water predates planets. By the time a star forms and a disk of material gathers around it, water is already present, locked into ice and vapor. As planets assemble, they inherit this molecular legacy in varying amounts. The question for Earth is not whether water was available, but how it arrived and how much was retained. One powerful clue comes from isotopes. Isotopes are variants of the same element with different numbers of neutrons. Hydrogen has a heavier isotope known as deuterium, containing one neutron instead of none. The ratio of deuterium to ordinary hydrogen in water varies depending on where and how that water formed. Harold Urey played a central role in bringing isotopic analysis into planetary science. His work demonstrated that isotopic ratios preserve information about formation conditions, acting as chemical fingerprints that survive long after environments change. By measuring the deuterium to hydrogen ratio in Earth's oceans and comparing it to that found in comets, asteroids and meteorites, scientists can test different origin scenarios. Early on, comets were considered prime candidates for delivering Earth's water. They are rich in ice and originate from the outer regions of the solar system. Impacts during the early bombardment phase could, in principle, have supplied vast quantities of water. However, measurements complicated this picture. Many comets exhibit deuterium to hydrogen ratios roughly twice that of Earth's oceans. This mismatch suggests that comets like those measured could not have been the sole source of Earth's water. Some comets show ratios closer to Earth's value, others differ significantly. The diversity implies multiple reservoirs of water with different histories. Attention then turned to asteroids, particularly carbonaceous chondrites. These meteorites contain water bound in minerals and exhibit isotopic ratios much closer to Earth's oceans. This suggests that water-rich asteroids may have contributed substantially to Earth's supply. The emerging picture is mixed. Earth's water likely came from multiple sources, delivered over extended periods. Some may have been inherited directly from the solar nebula, some delivered by asteroids, some perhaps by a subset of comets. None of these contributions can be isolated cleanly. This uncertainty is not a failure of measurement. It reflects the chaotic nature of planetary formation. Early Earth experienced countless impacts, exchanges of material, and episodes of heating and loss. Isotopic signatures were blended, altered, and partially erased. What remains are constraints, not certainties. Beyond Earth, isotopic analysis continues to shape understanding of water across the solar system. Mars shows evidence of ancient water loss through its enriched deuterium content. The Moon contains traces of water with signatures linked to both cometary and solar sources. Icy moons preserve water with compositions shaped by internal processing. Each body tells a slightly different story. Beyond the solar system, water has been detected in protoplanetary disks, in exoplanet atmospheres, and in cold interstellar space. Its presence is widespread, but its form and abundance vary enormously. This raises an important point. Water is common, liquid water is not. The conditions required for water to remain liquid over long periods are narrow. Temperature must fall within a specific range. Pressure must be sufficient. The planet must retain an atmosphere. Energy input must be balanced against loss. These constraints define habitability limits. A planet too close to its star loses water to space through photodissociation and atmospheric escape. A planet too far sees water freeze permanently. Too small, and gravity cannot hold an atmosphere. Too active, and internal heating may drive volatile loss. Water's chemistry is forgiving, its physics is not. Even where water exists, its state matters. Ice locked beneath kilometers of crust behaves differently from surface oceans. Supercritical water near magma chambers drives different chemistry than cold ice in shadowed craters. Habitability depends not just on the presence of water, but on its accessibility and stability. This is where uncertainty remains most pronounced. Exoplanet surveys reveal many worlds within so-called habitable zones, regions where liquid water could exist on the surface. Yet habitability zones are not guarantees. They define possibility, not outcome. Planetary history matters. Delivery history matters. Retention matters. Geological activity matters. Water alone does not determine habitability, but without it, habitability is severely constrained. This perspective tempers enthusiasm with realism. The universe is rich in water, but poor in conditions that allow it to behave in the ways life on Earth exploits. Liquid water on Earth persists not because water is rare, but because Earth occupies a stable niche that allows water to cycle without being lost. This niche is fragile on cosmic timescales. Earth's water inventory has likely changed over time. Some has escaped to space, some has been locked into minerals, some has been recycled through the mantle. The current oceans are a snapshot, not a permanent feature. Looking outward reinforces this humility. Water's presence beyond Earth does not imply familiarity. Its forms, histories, and roles vary. Each environment reshapes water's behavior, revealing new aspects of a substance already known to be adaptable. Astrochemistry shows that water forms easily. Planetary science shows that keeping it is hard. Between those two facts lies the story of habitability. Isotopic fingerprints allow reconstruction of parts of that story, but never the whole. Some information is irretrievably lost to mixing and time. This is not a reason for pessimism. It is a reminder of scale. Water's journey from interstellar clouds to planetary oceans spans billions of years. Along the way, chance encounters and physical constraints shape outcomes. Life, where it appears, arises within those constraints, not apart from them. Water beyond Earth therefore reframes familiar questions. Instead of asking whether water exists elsewhere, the deeper question becomes how it behaves, how long it persists, and under what conditions it remains accessible. Those questions do not yield simple answers. They yield ranges, probabilities, and limits, and in that uncertainty lies a clearer picture of water's role in the universe, not as a guarantee of life, but as a prerequisite whose presence opens doors without deciding what passes through them. Water is widespread, ancient, and resilient. Liquid water, in stable contact with complex chemistry, is rare. Understanding that distinction sharpens both scientific curiosity and perspective, as attention gradually turns from familiar oceans to the vast, varied reservoirs beyond Earth, each carrying its own incomplete history. After all the uncertainty, disagreement, and open questions, it is worth pausing to say what is not in doubt. Water may resist a complete theoretical description, but it is not mysterious in the sense of being poorly measured or loosely understood. On the contrary, many of its properties are among the most precisely characterized in all of science. The challenge lies in distinguishing between what is firmly established and what remains interpretive. Some facts about water are experimentally robust. They have been measured repeatedly, using different techniques, across different laboratories, and over long periods of time. These results do not depend on particular models or assumptions. They stand on their own. The molecular composition of water is one such certainty. Each molecule consists of 2 hydrogen atoms bonded to 1 oxygen atom in a bent geometry. The bond angles, bond lengths, and electronic structure are known to high precision. Spectroscopic measurements, quantum calculations, and scattering experiments all converge on the same picture. Water's polarity is equally secure. The uneven distribution of charge within the molecule has been measured directly and inferred through countless independent observations. This polarity underlies water's dielectric behavior, its solvent properties, and its interaction with electric fields. There is no debate about its existence or significance. Hydrogen bonding is also firmly established. The presence of directional transient attractions between neighbouring water molecules is supported by spectroscopy, neutron scattering, and thermodynamic measurements. The typical strength and lifetime of these bonds are well constrained, even if their collective behaviour remains complex. Bulk properties such as density, heat capacity, compressibility, surface tension, and boiling point are known with extraordinary accuracy. Water's density maximum near freezing, its expansion upon solidification, and its unusually high heat capacity are not theoretical claims. They are repeatable measurements. The same is true for water's phase behaviour under many conditions. The existence of multiple ice phases at different pressures, the conditions for supercritical water, and the general shape of the phase diagram are supported by decades of experimental work. While details continue to be refined, the broad structure is settled. There is also strong consensus on water's role in biological systems. It acts as a solvent for biochemical reactions, stabilizes charged and polar groups, facilitates proton transfer, and moderates temperature. These functions are demonstrated across biology, from enzymes to ecosystems. Where caution enters is in interpretation. Knowing that hydrogen bonds exist does not uniquely specify how they organize at any moment in liquid water. Knowing that water has certain bulk properties does not uniquely determine the microscopic arrangements that produce them. Multiple models can account for the same observations. This is where debate remains active. For example, there is consensus that liquid water exhibits short-range order. There is no consensus on how to describe that order most usefully. Some emphasize ice-like local structures. Others emphasize density fluctuations or network connectivity. Each approach captures aspects of reality, but none has exclusive claim. Similarly, there is agreement that water near surfaces behaves differently from bulk water. Molecules near membranes, proteins, or mineral interfaces are more ordered and less mobile. The extent, stability, and functional significance of this structuring remain under discussion. Claims of distinct phases of intracellular water are more controversial. While interfacial effects are well supported, extending them to large scale, long-lived alternative states remain speculative. Here, the discipline of separating observation from interpretation is essential. The same applies to modelling. There is no dispute that molecular dynamic simulations reproduce many properties of water remarkably well. There is also no dispute that different models disagree in important details. These disagreements reflect modelling choices rather than experimental inconsistency. Consensus exists on the limits of models, even if consensus does not exist on which model is best. This distinction matters. Scientific discipline does not require that all questions be settled. It requires clarity about which claims are supported by direct evidence and which depend on interpretation. Water science is disciplined precisely because it maintains this separation. When a measurement is robust, it is treated as such. When an interpretation is provisional, it is labelled accordingly. Disagreement is not smoothed over. It is documented, explored, and constrained. This approach prevents confusion between uncertainty and ignorance. There is temptation, especially with familiar substances, to assume that unresolved questions imply a lack of understanding. In the case of water, the opposite is true. The unresolved questions exist because the foundational measurements are so solid. The basic facts are not in question. What is in question is how best to connect them into a unified explanatory framework. This is an important distinction. Scientific progress often involves moving from description to explanation. Water has been described in extraordinary detail. Explaining how all those descriptions fit together is the remaining challenge. In the meantime, the reliability of water-related science remains high. Engineers design systems based on water's properties with confidence. Climate models incorporate its behavior successfully. Biologists depend on its chemistry daily. None of these fields are paralyzed by theoretical debate. They operate on what is known clearly. At the same time, researchers remain careful not to overextend conclusions. Claims about new phases, hidden order, or universal theories of liquid water are treated cautiously. Evidence is weighed. Alternatives are considered. This balance between confidence and restraint is a strength, not a weakness. It reflects an understanding that some systems demand layered explanations. Water may never be captured fully by a single model, but that does not prevent accurate prediction within defined domains. Knowing where certainty ends is part of knowing clearly. As attention turns toward unresolved questions, this foundation matters. It anchors speculation. It constrains imagination. It ensures that new ideas remain connected to measurable reality. The next steps in understanding water will not come from discarding what is known. They will come from building carefully on it. New experiments will probe faster timescales. New simulations will explore larger systems. New theoretical frameworks may offer different ways of organizing existing knowledge. Through all of this, the core facts remain steady. Water is a small molecule with a strong polarity. Its hydrogen bonds are weak individually but powerful collectively. Its bulk properties are anomalous but precisely measured. Its behavior supports life and shapes planets. These are not open questions. What remains open is how all of these truths coexist within a single, unified picture. Recognizing that distinction brings clarity. It allows science to move forward without pretending to finality. It acknowledges limits without surrendering rigor. It keeps curiosity grounded in evidence. Water, studied as carefully as any substance on Earth, teaches this lesson quietly. Understanding does not always end in closure. Sometimes it deepens into a clearer sense of where certainty lies, and where questions genuinely remain. That clarity is not an admission of defeat. It is the foundation from which unresolved questions can be approached honestly and patiently. What remains unresolved about water is not a collection of loose ends waiting to be tied up. It is a set of structural questions that arise naturally from how the system behaves. These questions persist not because of missing data or experimental failure, but because liquid water sits in a regime where familiar approaches lose traction. The difficulty is built into the problem itself. At the most basic level, there is still no universally accepted microscopic description of liquid water that explains all of its macroscopic properties at once. Many models reproduce some properties well. None reproduce all of them without compromise. This is not an accident. Liquid water exists in a densely interacting state where molecules are close enough to influence one another strongly, yet mobile enough to rearrange constantly. Interactions are directional, transient, and cooperative. No single interaction dominates. No single scale controls behavior. This places water in an awkward position relative to theory. For solids, long-lived order allows simplification. For gases, weak interactions do the same. Liquids, and especially water, occupy the middle ground where neither approach fully applies. One unresolved question is whether a unified theory of liquids is even possible in the way theories of gases or crystals are. A unified theory would provide a general framework capable of predicting liquid behavior from a small set of principles independent of specific molecular details. For decades, physicists have searched for such a framework. Progress has been uneven. Statistical mechanics offers powerful tools, but often requires approximations tailored to particular systems. Integral equation theories capture some correlations but struggle with strong directionality. Mode coupling approaches describe dynamics near glass transitions but are less effective for ordinary liquids. Water stresses all of these approaches simultaneously. Its hydrogen bonding introduces strong directional correlations. Its density anomalies reflect subtle balance between competing structures. Its dynamics involve collective rearrangements across multiple timescales. Whether these features can be subsumed into a single, compact theoretical description remains an open question. Some researchers argue that liquids may resist unification by nature. They suggest that liquids require system-specific descriptions, each tuned to the interactions involved. In this view, the absence of a universal liquid theory is not a temporary gap, but a reflection of how matter organizes itself in this regime. Others remain cautiously optimistic. They point to advances in soft matter physics, where concepts such as emergent behavior, scaling, and universality classes have helped organize complexity without eliminating it. They suggest that a unifying language may exist, even if it looks different from traditional theories. This debate is active, not speculative. International collaborations in soft matter physics, statistical mechanics, and chemical physics continue to explore these questions. Large research networks bring together experimentalists, theorists, and computational scientists to compare data across techniques and scales. Neutron scattering facilities, synchrotron light sources, and ultrafast laser laboratories contribute complementary views. High-performance computing centers enable simulations that were impossible a decade ago. None of this effort is idle. What remains unresolved is how to connect these views into a coherent whole. Another structural uncertainty concerns the nature of local order in liquid water. There is consensus that local structure exists. There is no consensus on how to characterize it most meaningfully. Some descriptions emphasize tetrahedral arrangements resembling fragments of ice. Others emphasize fluctuations in density or coordination number. Some models treat water as a mixture of locally distinct environments that interconvert. Others argue that such distinctions impose artificial categories on a continuous distribution. The question is not which description is correct in an absolute sense. The question is which description is most useful for explaining specific phenomena. This usefulness may vary by context. The same ambiguity appears in discussions of anomalies. Water's unusual properties cluster together in temperature and pressure space, but the underlying reason for this clustering remains debated. Are these anomalies manifestations of an underlying critical point at inaccessible conditions? Or do they arise from smooth shifts in local structure without sharp transitions? Evidence exists on both sides, none is decisive. This kind of uncertainty is structural. It reflects the fact that multiple mechanisms can produce similar macroscopic behavior. Distinguishing between them requires not only better data, but clearer criteria for what would count as resolution. Measurement limits also impose boundaries. Even with ultrafast spectroscopy and advanced scattering techniques, observations remain indirect. Signals must be interpreted through models. Models encode assumptions. Assumptions shape conclusions. This circularity is not unique to water, but it is amplified here because of water's responsiveness. Small changes in conditions produce measurable differences. Extracting general principles from such sensitivity is difficult. There are also unresolved questions about scale coupling. How do molecular level rearrangements propagate into mesoscopic and macroscopic behavior? How do local fluctuations influence bulk thermodynamics? How do short-lived hydrogen bond networks give rise to long-lived properties such as heat capacity and compressibility? These questions sit at the intersection of dynamics and thermodynamics, a region where traditional tools are still evolving. In biology, unresolved questions persist as well. Water's role inside cells is established in broad terms, but the details of how intracellular water participates in organization, transport and regulation remain under active investigation. The degree to which water structure influences biological function is not fully settled, nor is it likely to be captured by a single answer. Again, this is structural rather than accidental. Cells are heterogeneous, dynamic and crowded. Water within them reflects that complexity. Expecting a simple description may be unrealistic. Across all of these domains, one theme repeats. The unresolved questions do not point toward hidden secrets waiting to be uncovered. They point toward limits imposed by complexity, interaction, and scale. This matters for how uncertainty is framed. There's a tendency to treat unresolved questions as mysteries, implying that something fundamental is missing. In the case of water, what is missing may not be facts, but a form of explanation that matches the system's nature. Limits of knowledge here are not barriers to progress. They are boundaries that shape the kind of progress possible. Instead of closure, water science advances through constraint. Models become better bounded. Interpretations become more precise. Domains of applicability become clearer. This is already happening. Debates narrow as data accumulates. Extreme claims are tempered. Productive disagreement replaces confusion. The field does not drift. It converges slowly, not toward a single picture, but toward a clearer map of what can and cannot be said. This is a different kind of maturity. Understanding water may never culminate in a single unifying equation or theory. It may culminate in a structured understanding of regimes, mechanisms, and limits. Such an outcome would not diminish science, it would refine it. Water forces a reconsideration of what it means to explain a system. It suggests that explanation may sometimes consist of layered descriptions, each valid within its scale, connected by careful reasoning rather than reduction. Recognizing this does not end inquiry, it redirects it. The unresolved questions surrounding water are not signs of failure or neglect. They are indicators that the system sits at the edge of what current frameworks were designed to handle. That edge is where new ideas tend to form. As research continues, water will remain a testing ground for theories of complexity, emergence, and collective behavior. It will continue to expose assumptions and challenge simplifications, not because it is unknowable, but because it is densely interactive, multiscale, and persistently in motion. Those qualities do not make water mysterious. They make it instructive. And as attention shifts towards synthesis, these unresolved questions provide the structure around which understanding can deepen, without the expectation that it must ever fully settle. Water invites familiarity. It fills glasses, clouds the air, carves valleys, and flows through living cells. It feels ordinary enough to disappear into daily life. And yet, as this journey has shown, it is also the most studied substance science still does not fully understand. That tension is not a failure of investigation. It is a lesson about how knowledge works. Water demonstrates that understanding does not always move toward neat completion. Sometimes it moves sideways, outward, and deeper at the same time. Measurements become more precise. Models become more sophisticated. Explanations become more careful, but closure remains out of reach, not because something is missing, but because the system itself resists being compressed into a final summary. This is where scientific humility becomes a strength. Humility does not mean uncertainty about facts. The facts about water are among the most reliable in science. Its molecular structure, its polarity, its hydrogen bonding, its bulk properties, and its role in life and climate are all known with extraordinary confidence. What humility recognizes is the difference between knowing properties and fully unifying them. Water sits at the intersection of many scales at once. Electronic structure influences hydrogen bonding. Hydrogen bonding shapes molecular networks. Networks influence thermodynamics. Thermodynamics feeds into planetary behavior. No single level governs the rest. Each participates. Because of this, explanation becomes layered rather than final. A model may explain water's density anomaly. Another may explain its dielectric behavior. Another may capture its dynamics under pressure. None are wrong. None are complete. Science advances not by pretending these partial views are final, but by holding them together honestly. This is what makes water such a valuable case study. It reveals the limits of reductionism without rejecting it. It shows how collective behavior can emerge from simple components without being reducible to them. It demonstrates that complexity can be lawful, reproducible, and measurable without being simple. In that sense, water teaches restraint. It encourages science to say, clearly and confidently, what is known, and to say, just as clearly, what remains open. It reminds us that unanswered questions are not always temporary gaps. Sometimes they reflect the shape of the problem itself. This does not weaken knowledge, it strengthens it. When science acknowledges limits, it avoids false certainty. When it distinguishes measurement from interpretation, it stays grounded. When it accepts that some systems demand multiple descriptions, it becomes more accurate, not less. Water, studied across centuries and disciplines, continues to reward this approach. Each advance sharpens understanding while revealing new structure. Each refinement clarifies behavior without exhausting it. This is not an unfinished story waiting for a final chapter. It is a stable, evolving understanding that grows by constraint rather than conquest. To know water well is not to hold it still. It is to understand how it moves, interacts, and resists simplification. In that way, water reflects something broader about science itself. Knowledge does not always end in completion. Sometimes it ends in balance, a clear sense of what is known, a careful respect for what is not, and the confidence to keep both in view at the same time. That balance is not uncertainty. It is understanding without the need for closure. And for a substance so ordinary, that lesson may be one of water's most enduring contributions.